You can survive a bullet, a fall, even the vacuum of space. But there is one thing no human body survives, no matter how perfect the technology: speed. What would the universe actually do to you if you tried to reach the speed of light? Getting close to that speed does not just challenge physics, it turns the cosmos into something that actively, systematically destroys you. If you are the kind of person who is curious about the real science behind the biggest questions in existence, make sure to subscribe to the channel. Now let's get started. As you accelerate, as you push your spacecraft faster and faster toward the speed of light, something deeply strange happens to the energy required to keep accelerating. It does not just increase. It increases in a way that curves upward toward infinity. The closer you get to light speed, the more energy you need to go just a little bit faster. And as you approach the final threshold, as you get to 99%, then 99.9%, then 99.99%, the energy required approaches infinity itself. You cannot carry infinite energy. No fuel tank in any universe could hold it. No engine could produce it. The numbers simply do not allow it. This is not an engineering problem. This is a fundamental property of space-time. Physicists have actually observed this directly. At CERN, the European Organization for Nuclear Research, inside the Large Hadron Collider beneath the border of France and Switzerland, protons are accelerated to about 99.9% of the speed of light. And to push those tiny subatomic particles to that speed, particles that have essentially no mass compared to you, the collider uses enough electrical energy to power a small city. For protons, particles so small that it takes roughly 10 to the power of 27 of them to make up a single kilogram of matter. And even with all of that energy, even after decades of engineering refinement, those protons still do not reach the speed of light. They get extraordinarily close, but they never cross that line. So if you tried to reach light speed, the energy required would be so astronomically beyond anything conceivable that the question stops being an engineering question and becomes a philosophical one. But here is the thing: the impossibility of actually reaching light speed is almost the least interesting part of this story, because even if we imagine, just for the sake of the journey, that you somehow got close, that you reached 99% or 99.9%, the universe does not wait for you to reach 100% before it starts punishing you. It starts long before that, and what it does to you is far more creative, far more terrifying, and far more beautiful in its cold mathematical logic than anything you might expect. Speaking of journeys through space that sound impossible until you dig into the real physics, if you have not yet watched my video on what would actually happen on a journey to Proxima Centauri, I genuinely think you should go check it out after this one on the card above, because that video takes everything we are covering here and puts it into the context of a real destination and what a crewed mission there would actually face. It pairs perfectly with what we are exploring today. The link is in the description and pinned on the comments. Now, back to the destruction, let us talk about something called the interstellar medium. Space, as most people imagine it, is empty, a perfect vacuum, nothing between the stars, and in a casual sense that is not entirely wrong. Interstellar space is far, far less dense than anything we experience here on Earth, but it is not empty, not truly. Between the stars, scattered across the vast distances of the galaxy, there are atoms, mostly hydrogen. About 1 atom per cubic centimeter on average, one lonely hydrogen atom for every cubic centimeter of space. That is extraordinarily sparse. At rest, or even at slow speeds, those atoms are utterly harmless. You would pass through them and never know they were there. But speed changes everything. When you are traveling at, say, 90% of the speed of light, at roughly 269,800 kilometers per second, Those sparse, harmless hydrogen atoms are no longer slow, gentle particles drifting in the void. From your perspective, they are slamming into your spacecraft at 90% of the speed of light. The energy of each individual impact transforms. What was once a harmless atom becomes, in effect, a high-energy cosmic ray particle, and at 99.9% of the speed of light. Each hydrogen atom your craft encounters carries enough energy, upon impact, to be genuinely damaging at the subatomic level. Your hull, whatever material it is made of, begins absorbing radiation doses that, over even a short journey, would be lethal to any living thing inside. The interstellar medium, the stuff that was so thin and harmless that astronomers sometimes describe space as a vacuum, becomes a wall of radiation, a constant, invisible, deadly stream of particle impacts, each one converted by your own velocity into a miniature cosmic ray event. And this is just from the hydrogen. We have not even talked about what happens to the light itself. Because what happens to light, to the photons you encounter as you accelerate toward that limit, is perhaps the most visually dramatic and scientifically fascinating part of this entire story. And that is exactly where we are going next. We are going to talk about what you would actually see from inside that spacecraft as the universe in front of you begins to transform. And it is going to start beautifully and end in something that should make you feel the full weight of how extraordinary, how dangerous, and how humbling the cosmos truly is. Let us talk about what you would see, because before the universe kills you, it puts on a show, and it is one of the most breathtaking, alien, deeply unsettling visual experiences that physics permits. No drug, no dream, no special effect in the history of cinema comes close to what your eyes would actually witness as your spacecraft climbs toward the speed of light. And the reason it looks the way it does has everything to do with the nature of light itself, with what photons are, how they behave, and what velocity does to the relationship between you and the electromagnetic radiation flooding the cosmos. So close your eyes for a second. Picture yourself at the front of the spacecraft, looking out through a viewport, stars in every direction, the familiar sky, the Milky Way stretching across the black like a river of ancient light. It is still, it is quiet, it is beautiful in the way that only deep space can be beautiful, that particular silence that makes you feel both incredibly small and incredibly alive at the same time. Now the engines ignite. At first, nothing dramatic. At 10% of the speed of light, about 29,979 kilometers per second, the stars ahead of you begin to shift. Very subtly, almost imperceptibly, they seem to drift just slightly toward the front of your view, like rain on a windshield that appears to fall toward you when you are driving rather than straight down. This is a phenomenon called aberration of light, and it is one of the first signs that the universe is beginning to respond to your velocity. Aberration is actually not new knowledge. It was first observed by the English astronomer James Bradley back in 1728, when he noticed that the apparent positions of stars shifted slightly depending on the direction Earth was moving in its orbit around the Sun. He was not traveling anywhere near light speed. Obviously, Earth moves at about 107,000 kilometers per hour, but even that relatively gentle motion was enough to produce a measurable shift in stellar positions. Bradley had stumbled onto a real physical consequence of the finite speed of light, and it told astronomers something profound. Light does not arrive instantaneously, it takes time, and that time interacts with motion in ways that distort what we see. At your hypothetical 10% of light speed, the aberration is noticeable but manageable. The star field in front of you is slightly denser than behind. Stars are bunching forward, but the colors are still recognizable. The sky still looks like a sky. Keep accelerating. At 50% of the speed of light, 149,800 896 kilometers per second, the visual shift becomes dramatic. The stars ahead of you are no longer gently drifting forward. They are being pulled toward the center of your view, like water circling a drain. The entire stellar panorama is compressing itself into a shrinking circle directly in front of your spacecraft. What was spread across the entire sky is now crowding into a cone, and behind you, darkness, a growing, spreading region of black where the stars used to be, because the light from those stars can barely keep up with you anymore. You are racing away from the photons trying to reach your eyes from behind. And the colors, oh, the colors are changing. This is where something called the Doppler effect comes in, a concept most people know from sound, from the way an ambulance siren rises in pitch as it approaches and drops as it moves away. The same thing happens with light. When you move toward a light source, the waves of that light get compressed. Compressed waves mean higher frequency. Higher frequency means a shift toward the blue end of the visible spectrum. This is called blue shift. When you move away from a light source, the waves stretch out. Lower frequency, a shift toward the red end. Redshift at 50% of light speed, the stars directly ahead of you are significantly blue shifted. Stars that would normally appear yellow or orange now look white or pale blue. Stars that were already blue now push into frequencies beyond the visible spectrum, into ultraviolet. Your eyes, evolved for a very specific window of the electromagnetic spectrum here on the surface of Earth, are starting to lose stars. They are shifting out of the range you can see, climbing into invisible territory. And behind you, the reverse is happening. Stars are redshifting. Red stars become infrared. Infrared becomes invisible. The darkness behind you grows. This is still, in its own terrifying way, beautiful. There is a real majesty to it. You are watching the universe bend around your velocity. You are seeing physics happen in real time. Every photon that reaches your eyes is a messenger from the cosmos, and the message it carries is being distorted by the sheer fact of how fast you are moving, but keep accelerating because beauty does not last. At 90% of the speed of light, 269,812 kilometers per second, the sky ahead of you has transformed into something your brain was never built to process. Almost all of the stars that were once spread across the entire sky have now been compressed into a small, intensely bright circle directly in front of you. The rest of the sky, the vast majority of your field of view in every other direction, is black, empty. The stellar light that should be coming from the sides and behind cannot reach you anymore. You have outrun it, but that circle ahead of you, that is not just bright, it is violent. The blue shift has become extreme. Visible light from those stars has been pushed so far up the electromagnetic spectrum that a significant portion of it is now arriving as ultraviolet radiation, X-rays, and even gamma rays. Radiation that passes right through ordinary glass, radiation that passes right through ordinary hull materials, radiation that passes through human tissue and damages DNA at the cellular level. You are no longer looking at starlight. You are looking into a focused beam of cosmic radiation, and it is aimed directly at you. And here is the detail that I want you to hold on to, because it matters enormously to the bigger picture of this story. The electromagnetic spectrum does not end at gamma rays, but for practical purposes at these energies, what is hitting your spacecraft is some of the most damaging radiation in the known universe. The kind of radiation we detect coming from supernovae, from neutron star mergers, from the most violent astrophysical events imaginable, and you are generating it yourself. With your own velocity, you are turning the gentle light of distant stars into weapons simply by moving fast enough. The radiation shielding you would need to survive at 90% of light speed would need to be extraordinary. And we are not there yet. We are still accelerating at 99% of the speed of light. Something changes that goes beyond just the visuals. Up until this point, we have been talking about what you see. But special relativity, Einstein's great gift to human understanding, has more to say. Because as your velocity approaches the speed of light, the fabric of space and time itself begins to behave differently around you. Two of the most profound and well-tested predictions of special relativity are time dilation and length contraction. These are not metaphors, they are not philosophical abstractions, they are measurable, confirmed, real physical phenomena that have been verified repeatedly with atomic clocks, with particle accelerators, with astronomical observations. They happen. They are happening right now to every object moving through space, including you, sitting wherever you are, though at speeds so low that the effect is completely negligible in daily life. But near the speed of light, the effects become enormous. Time dilation means that time passes more slowly for a moving object relative to a stationary one. The faster you move, the slower your clock ticks compared to a clock left behind on Earth. At 99% of light speed, your clock runs at roughly 1/7 the rate of a clock on Earth. Every second you experience, 7 seconds pass back home. You are aging more slowly than everyone you left behind, not metaphorically, physically, measurably. Your cells divide more slowly. Your heartbeat happens less frequently. Relative to Earth time, you are living in a different flow of time. This is not just theoretical. In 1971, physicists Joseph Hafele and Richard Keating flew cesium atomic clocks around the world on commercial airliners and compared them to stationary clocks on the ground. The flying clocks measured a different amount of elapsed time. The difference was tiny. We are talking nanoseconds, but it matched the predictions of relativity almost exactly. The experiment has been repeated many times since with increasing precision, and the result is always the same. Motion changes time. GPS satellites, the very technology your phone uses to navigate, have to account for relativistic time dilation in their programming. The satellites move fast enough relative to Earth's surface and exist in a weaker gravitational field, which also affects time, that without relativistic corrections, GPS systems would accumulate errors of roughly 11 kilometers per day. Every time you use a map app, you are benefiting from Einstein's understanding of space-time. So time dilation is real, it is confirmed, it is built into technology you use every day. And at 99% of light speed, it is not a small correction anymore. It is a fundamental feature of your experience. Dilength contraction is the other side of the same coin. Just as time stretches out for a stationary observer watching you fly by, space itself, the distance between you and your destination, contracts in the direction of your motion. At 99% of light speed, the 4 light-years between Earth and Proxima Centauri, our nearest stellar neighbor, would appear to you to be compressed to roughly half a light-year. The universe, from your perspective, is physically shorter in the direction you are traveling. Agon, not a metaphor, not an illusion, a real physical measurable compression of the spatial dimension aligned with your velocity. This means that if you could actually reach near light speed, the journey would feel much shorter to you than it would appear from Earth. You might experience only months passing while years tick by back home. You might arrive, if you arrived, having aged only a fraction of what your family and friends back on Earth had aged. The universe is strange. The universe is deeply, profoundly strange. And the closer you get to its speed limit, the stranger it becomes. But none of this strangeness protects you from what is coming, because we have been talking about light and time and beautiful physics. And now I need to bring you back to the physical reality of your body in that spacecraft, hurtling through a cosmos that is doing everything it can, within the laws of physics, to stop you. We talked briefly about the interstellar medium. about hydrogen atoms becoming cosmic ray particles at high velocity, but I want to go deeper into what that actually means for the structure of your spacecraft, because the numbers, when you actually work them out, are sobering in a way that is hard to put into words. At 99% of the speed of light, each hydrogen atom you encounter, each single proton floating in the void between the stars, hits your spacecraft with a kinetic energy of roughly 1 billion electron volts, 1 GeV, in the language of particle physics. That is the energy scale of high-energy cosmic rays, the kind of radiation that comes from supernova shock waves and active galactic nuclei, the kind of radiation that, on Earth, is stopped by our planet's magnetic field and atmosphere before it ever reaches the surface. You have no planet. You have no magnetic field strong enough. You have your hull. At interstellar hydrogen densities, roughly 1 atom per cubic centimeter, a spacecraft traveling at 99% of light speed would be encountering millions upon millions of these collisions every second across its forward cross-section. The cumulative radiation dose absorbed by anything inside, human tissue, electronics, structural materials, would be catastrophic over any meaningful distance, and we have only been talking about the hydrogen. The interstellar medium also contains helium atoms, dust grains, molecular clouds, and occasional denser regions where the particle count is significantly higher. Each one of those encounters at near-light speed carries energy that can shatter atomic bonds, ionize molecules, and physically erode your hull at the subatomic level. Your spacecraft is being sandblasted by the universe itself. And yet, and this is the part I find most breathtaking about all of this, none of these obstacles have stopped humanity from dreaming, from calculating, from asking whether there is a way around these walls of physics, whether the universe, as brutally honest as it is about the rules, might have left a door somewhere, a loophole, a cosmic secret passage written into the mathematics that we simply have not found yet. That conversation about warp drives, about exotic matter, about the Alcubierre metric, and what physicists genuinely think about the future of interstellar travel is one of the most fascinating in all of modern science, and it is exactly where this story is going. But before we get there, we need to talk about something that sits at the absolute heart of why light speed is the limit it is, something that connects quantum mechanics, general relativity, and the deep structure of space-time in a way that most people have never heard explained. We need to talk about what mass actually is, and what happens to it as you approach the speed of light, because the answer is not what most people expect, and it changes everything. If you are enjoying this journey, make sure to subscribe to the channel. Every day, we go deep into astronomy, astrophysics, and cosmology, and we do it in a way that actually makes sense. You belong here. Let us talk about mass, not weight, not size, not the number on a scale, mass, the actual, fundamental property of matter that determines how strongly the universe resists changing your state of motion, the thing that makes you you, in a physical sense, the thing that anchors you to reality. Because here is a question that sounds simple but turns out to be one of the deepest in all of physics. Why does anything have mass at all? For most of human history, mass was just accepted. Things have it. Some things have more of it than others. You push something heavy, it resists. You push something light, it moves easily. Newton codified this into his laws of motion in 1687, and for over 2 centuries, mass was simply a number you plugged into equations. Nobody asked where it came from. It was just there. Then in the 20th century, everything changed. 2 revolutions happened almost simultaneously. Einstein gave us relativity, which rewrote the relationship between mass, energy, space, and time. And quantum mechanics gave us an entirely new picture of what matter is made of at its most fundamental level. And when physicists eventually managed to connect those 2 frameworks, after decades of work, after building some of the most complex experimental apparatus in human history, what they found about the origin of mass was genuinely shocking. It changed what the word mass even means. Let us start with Einstein, because his contribution here is the one most people have heard of, even if they have never really understood what it means. E equals mc squared, 4 symbols, the most famous equation in science, printed on posters, carved into monuments, repeated in films and books and classrooms around the world, and almost universally misunderstood. What it actually says is this: energy and mass are not two separate things. They are two faces of the same thing. They are interchangeable. They are, at the deepest level of physical reality, the same substance expressed in different forms. The c squared in the equation, c being the speed of light, approximately 299,792 kilometers per second, is simply the conversion factor between the two. And because c is such an enormous number and c squared is that enormous number multiplied by itself, the equation tells us something staggering. Even a tiny amount of mass contains an almost incomprehensible amount of energy. 1 single kilogram of matter, fully converted to energy, would release approximately 89.8 petajoules. That is roughly the energy released by 21 megatons of TNT. The bomb dropped on Hiroshima in 1945 released energy equivalent to the complete conversion of about 1 gram of mass. 1 gram. The mass of a small paperclip, and it leveled a city. This equivalence is not theoretical anymore. It is the operating principle behind nuclear reactors, which power hundreds of millions of homes around the world. It is observed in particle accelerators every day. It is happening in the core of our sun right now, where hydrogen nuclei fuse into helium, and the tiny difference in mass between the inputs and outputs is released as the light and heat that makes all life on Earth possible. Every photon of sunlight that has ever touched your skin is the direct product of mass being converted into energy. E equals mc squared is not just an equation. It is a description of how the sun keeps shining. It is the reason you are alive, but here is where it connects directly to our story, to light speed, to what happens to you as you accelerate. That equation has a fuller form, a version that Einstein actually wrote, which most textbooks leave out because it is slightly more complex, but which tells a richer and more important story. The full relativistic energy equation includes a factor called the Lorentz factor, usually represented by the Greek letter gamma. And the Lorentz factor is a mathematical expression that depends entirely on your velocity relative to the speed of light. At low speeds, the speeds we experience in everyday life, the Lorentz factor is essentially 1. It barely changes anything. The full equation collapses back to the familiar form, and Newtonian physics works just fine. This is why you do not need to account for relativity when you throw a ball or drive a car. The corrections are so tiny at those speeds as to be completely irrelevant, but as your velocity increases toward the speed of light, the Lorentz factor begins to climb. Slowly at first, then faster still, and as it climbs, something happens to your effective mass, the mass that the universe has to push against to keep accelerating you. That is deeply, deeply counterintuitive. It increases. Not because matter is being added to you, not because you are eating or gaining weight in any conventional sense, but because energy and mass are the same thing, and as you pour more and more energy into accelerating, that energy itself contributes to your effective inertia. The kinetic energy of your motion adds to your effective mass, and that increased effective mass requires even more energy to accelerate further, which adds more effective mass, which requires more energy still. It is a runaway loop, a feedback cycle built into the mathematics of space-time, and it spirals toward infinity as your velocity approaches the speed of light. At 90% of light speed, your effective mass is about 2.3 times your rest mass. You are, in a physical sense, more than twice as hard to accelerate as you were at rest. At 99% of light speed, your effective mass is about 7 times your rest mass. At 99.9%, it is about 22 times your rest mass. At 99.99%, it is about 224 times your rest mass. At 99.999%, it is over 700 times your rest mass. See the pattern. Each additional 9 you add after the decimal point multiplies the energy requirement dramatically. You are in an asymptotic race toward infinity, always getting closer, always requiring more, never arriving. The speed of light sits at the end of that progression like a wall that keeps retreating, because every step you take toward it makes the next step geometrically harder. This is not an engineering problem. This is not a funding problem. This is mathematics telling you in the clearest possible language that the speed of light is not a barrier you push through. It is a boundary woven into the structure of reality itself. Now, here is where the story takes a turn that I genuinely love, because it moves from the very large to the very small, from cosmology and spacecraft and light years down into the quantum world, down to the level where reality stops looking like anything you can picture and starts behaving in ways that challenge every intuition you have ever built up about how things work. We talked about the origin of mass, about why things resist acceleration. But I said earlier that the 20th century brought a second revolution, quantum mechanics, and that when physicists eventually connected relativity to quantum theory, what they found about mass was shocking. That connection is called quantum field theory, and the discovery it led to, confirmed in 2012 by one of the greatest experimental achievements in the history of science, is the Higgs mechanism, the Higgs field. You have probably heard the name. The Higgs boson made headlines around the world when it was detected at CERN's Large Hadron Collider in July of 2012. Physicists Peter Higgs and Francois Englert, who had theoretically predicted its existence back in 1964, received the Nobel Prize in Physics the following year. It was a moment of genuine triumph, a prediction made nearly 50 years earlier, finally confirmed by an experiment involving thousands of scientists from over 100 countries, working with a machine 17 kilometers in circumference buried beneath the ground on the border of France and Switzerland. But what is the Higgs field? And what does it actually do? Imagine that all of space, every cubic centimeter of the universe from here to the most distant galaxy we have ever detected, is filled with an invisible field, not a force field in the science fiction sense, a quantum field, a fundamental feature of space-time itself, like a cosmic ocean that permeates everything everywhere at all times. This is the Higgs field. Most particles, as they move through space, interact with this field. They do not just pass through it cleanly, they couple to it, they drag against it in a sense. And that resistance, that coupling between a particle and the Higgs field, is what we experience as mass. Mass is not an intrinsic property that particles carry around with them like a label. Mass is a dynamic interaction. It is the result of particles pushing through a field that fills all of space. Different particles couple to the Higgs field with different strengths. The top quark, the heaviest known fundamental particle, couples very strongly, which is why it is so heavy. The electron couples very weakly, which is why it is so light. And photons, particles of light, do not couple to the Higgs field at all. They pass through it with zero interaction, zero resistance, zero mass. And that last point is the key to everything, because that is precisely why light travels at the speed it does. Photons have no mass. They do not interact with the Higgs field. There is nothing to resist their motion through space. So they travel at the maximum speed that the structure of space-time allows, the speed of causality, the speed at which information and influence can propagate through the universe. We call it the speed of light, but it would be more accurate to call it the speed of massless particles or the speed of spacetime itself. You, on the other hand, are made of quarks and electrons. You are built from particles that interact strongly with the Higgs field. Your mass is real, your inertia is real, and that means no matter how hard you push, no matter how much energy you pour into your engines, you can never fully overcome the resistance that comes from being made of matter. In a universe threaded with the Higgs field, the speed of light is not just a number, it is the signature of masslessness. And you are not massless, you never will be. This is the moment in the story where I always feel something shift, where the physics stops feeling like an obstacle and starts feeling like a portrait. Because what we are really describing when we talk about mass and the Higgs field and the speed of light is the deep architecture of the universe. The rules that had to be exactly the way they are for anything to exist at all. If photons had mass, even a tiny negligible amount, light would travel slightly slower than it does. Electromagnetic forces would behave differently at large distances. Chemistry would change. Stars would burn differently. The periodic table of elements as we know it would not exist. And complex molecules, the kind that fold into proteins, that encode genetic information, that build nervous systems and eyes and brains, would never have formed. The fact that the Higgs field gives mass to matter particles but leaves photons untouched is not an accident of cosmic luck. It is a structural feature of reality without which you and I and every living thing that has ever existed would be impossible. You cannot reach the speed of light. But you exist because of the same physics that makes that true. There is something in that worth sitting with. Now let us come back down to the spacecraft. Because we have been in the quantum world, in the realm of fields and fundamental particles, and it is time to bring all of that abstract beauty into sharp physical contact with the reality of what a near-light speed journey would actually do to your body. We talked about radiation, about the interstellar medium becoming a wall of particle impacts, about blue shift turning starlight into gamma rays. But there is another physical consequence of near-light speed travel that almost nobody talks about, and it is in some ways the most viscerally disturbing of all of them. It is called Unruh radiation, predicted theoretically in 1976 by physicist William Unruh. Unruh radiation is a consequence of quantum field theory in accelerating reference frames. In simple terms, it says this: when you accelerate through space, the quantum vacuum, the fabric of space-time itself, which at the quantum level is not truly empty but seething with virtual particle activity, appears to you to be a warm bath of thermal radiation. A stationary observer in space sees nothing. The quantum vacuum looks cold and empty to them. But an accelerating observer, someone pushing their spacecraft faster and faster, experiences that same vacuum as a thermal field, as heat, as real, physical radiation with a temperature that depends directly on the rate of acceleration. Now, for any acceleration we can currently achieve, for any rocket or spacecraft we have ever built, the Unruh temperature is so incredibly small as to be essentially unmeasurable. We are talking about fractions of a billionth of a degree above absolute zero, completely negligible. But to reach speeds approaching the speed of light in any reasonable amount of time, in years rather than millennia, you would need to maintain an enormous rate of acceleration. And at those acceleration rates, the Unruh temperature begins to climb into ranges that are physically significant. Some theoretical calculations suggest that at extreme accelerations, the Unruh effect could contribute meaningfully to the radiation environment inside the spacecraft. You would be generating heat, generating radiation out of the fabric of empty space, out of nothing, simply by accelerating. The universe, it turns out, does not just passively resist you reaching its speed limit. It actively heats up around you as you try. And here is where all of these threads, the relativistic mass increase, the radiation from the interstellar medium, the blue shift of starlight into gamma rays, the Unruh effect, the Higgs field, the energy requirements that climb toward infinity, come together into a single unified picture, a picture that says something profound not just about physics, but about the nature of the cosmos we inhabit. The universe is not hostile. It is not trying to stop you out of cruelty or indifference. It is structured, deeply, elegantly, almost incomprehensibly structured, and that structure has consequences. Every rule that makes light speed unreachable is the same rule that makes stable atoms possible, that makes chemistry work, that makes stars ignite and burn for billions of years, that makes planets form and cool and grow oceans, that makes evolution possible, that made you possible. The speed of light is not a wall, it is a signature, a watermark pressed into the fabric of reality by the same deep physics that assembled you from stardust 4.5 billion years after the Big Bang. You are not kept from the stars by a cruel universe. You are kept from the stars by the same laws that built you out of them. But, and this is the part that keeps physicists and dreamers awake at night, those laws have edges, places where they become ambiguous, where they seem to allow things that should not be possible, where the mathematics opens strange doors that nobody has yet managed to either walk through or conclusively close. We have talked about why you cannot travel through space at the speed of light. But what about bending space itself? What about moving your destination toward you rather than moving yourself toward your destination? What about the theoretical frameworks that have been sitting in the physics literature for decades, taken seriously by real researchers at real institutions, that suggest the light speed limit might be navigable after all, not by breaking the rules, but by finding the one exception they seem to permit? That is the conversation that is coming. And it involves a physicist named Miguel Alcubierre, a concept called exotic matter, and a set of equations that NASA has actually spent resources investigating. It also involves some of the most honest uncertainty in modern science, researchers willing to say out loud that they do not know if this is possible, that the mathematics allows it, but the physics might not, and that the difference between those two things is one of the deepest open questions in the field. Let us talk about cheating, not breaking the rules, not ignoring the physics, not hand-waving away the mathematics with science fiction convenience, real, legitimate, peer-reviewed, published in serious journals cheating. The kind of cheating that starts with a genuine loophole in Einstein's own equations and ends with one of the most controversial and fascinating research programs in modern theoretical physics. Because here is the thing about the speed of light limit that most people never hear. It applies to objects moving through space. It says nothing, absolutely nothing, about space itself moving. Ride that again. Let it settle. The cosmic speed limit governs the motion of matter and energy through the fabric of space-time. But the fabric itself, space-time can expand, contract, curve, and stretch without violating any known law of physics. We know this because it is already happening right now, all around us. On the largest scales of the cosmos, space is expanding. Galaxies are receding from each other, not because they are moving through space at high speed, but because the space between them is growing. Some galaxies are moving away from us at recession velocities that exceed the speed of light, not because they are traveling faster than light through space, but because the space between us and them is expanding fast enough to carry them beyond our cosmic horizon. This is not speculation. This is one of the best confirmed observational facts in all of cosmology. Edwin Hubble first measured the recession of galaxies in 1929. Decades of subsequent observations, culminating in the stunning discovery, in 1998 by two independent teams of astronomers that the expansion of the universe is actually accelerating, have confirmed the picture beyond any reasonable doubt. The teams behind that discovery, led by Saul Perlmutter, Brian Schmidt and Adam Reis, received the Nobel Prize in Physics in 2011. Space stretches, space moves, and the speed of light says nothing about how fast it can do so. In 1994, a Mexican theoretical physicist named Miguel Alcubierre was sitting with Einstein's field equations, the mathematical heart of general relativity, the framework that describes how mass and energy curve space-time, and he asked a question that was either brilliant or absurd depending on your perspective. What if you could compress space in front of a spacecraft and expand space behind it? If space contracted ahead of you, your destination would move toward you. If space expanded behind you, your starting point would recede. The spacecraft itself would sit in a kind of bubble, a region of flat, undistorted space-time, and would not technically be moving through space at all. It would be carried by space, like a surfer riding a wave. The surfer does not move through the water at the wave's speed. The water moves, and the surfer goes along for the ride. Alcubierre worked through the mathematics carefully and published his result in the journal Classical and Quantum Gravity. What he found was that Einstein's equations actually permit this kind of spacetime geometry. The math works. There is a solution, now called the Alcubierre metric, or more popularly the Alcubierre warp drive, that describes a bubble of flat space-time moving through a distorted surrounding space at any arbitrary velocity, in principle, including velocities faster than light. No passenger inside the bubble would experience any acceleration, no relativistic mass increase, no time dilation relative to the outside universe, or at least, no inevitable time dilation in the way a moving particle experiences it. No radiation wall from the interstellar medium, because the spacecraft is not moving through the medium. The medium is flowing around the bubble. None of the horrors we have been describing for the past 3 parts apply to the interior of the warp bubble. From inside, you would feel nothing. You would sit in your ship, drink your coffee, and watch your destination approach. Because space itself is bringing it to you. It sounds too good to be true, and in several important ways it is, but not in the ways you might expect. The problems with the Alcubierre drive are real, significant, and fascinating. And I want to go through them honestly, because this is exactly the kind of place where science demands intellectual honesty, where we have to distinguish between what the mathematics permits and what physical reality might actually allow. The first problem is energy. To create the kind of space-time distortion the Alcubierre metric requires, to contract space ahead of the bubble and expand it behind, you need an exotic form of energy with negative energy density. Physicists call this exotic matter, and it is one of the most contentious concepts in theoretical physics. Negative energy density sounds like pure fantasy. But here is the remarkable thing. Negative energy is not entirely without physical precedent. Something called the Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed in 1997, demonstrates that in the tiny gap between two uncharged metal plates placed extremely close together, the quantum vacuum produces a measurable negative energy density relative to the surrounding space. The effect is tiny, extraordinarily tiny, but it is real, it has been measured, it exists. The question is whether negative energy can be harnessed, concentrated, and engineered at the scale required for an Alcubierre drive. And here the numbers become sobering in the extreme. Alcubierre's original calculations suggested that creating a warp bubble large enough for a spacecraft, say 10 meters in diameter, would require an amount of exotic negative energy roughly equivalent to the total mass energy of the planet Jupiter, converted entirely to exotic matter. which we do not know how to make, collect, or store. Jupiter has a mass of approximately 1.9 times 10 to the power of 27 kilograms. That is about 317 times the mass of Earth. The energy equivalent of that mass via E equals mc squared is a number so large that writing it out in standard notation takes up most of a line of text, and all of that in exotic form just to move a 10-meter bubble through space. That is not an engineering challenge. That is a civilization-scale impossibility with our current understanding of physics. But the story does not end there, because theoretical physics is a living enterprise. Problems get examined, assumptions get challenged, and in the years following Alcubierre's original paper, other physicists began refining the idea, looking for ways to reduce the exotic matter requirement without destroying the basic concept. In 1999, physicist Harold White at NASA's Johnson Space Center began working on modifications to the Alcubierre geometry. By changing the shape of the warp bubble from a simple sphere to a more complex, oscillating toroidal structure, a shape roughly like a donut, White calculated that the exotic matter requirement could potentially be reduced by many orders of magnitude. His revised estimates, published around 2012, suggested that a modified warp field might require exotic matter with a mass equivalent to only a few hundred kilograms rather than a Jupiter mass. These calculations generated enormous excitement in the popular science press. Headlines proclaimed that NASA was working on a warp drive, and in a narrow technical sense, that was not entirely wrong. White was leading a small research effort at the Johnson Space Center called the Advanced Propulsion Physics Laboratory, informally known as EagleWorks, which was examining these theoretical frameworks alongside other unconventional propulsion concepts. But it is important to be precise about what that means. A small team of researchers examining the theoretical possibility of exotic propulsion is very different from NASA building a warp drive. The EagleWorks lab was a legitimate scientific inquiry at the margins of what is currently understood. It was exactly the kind of speculative, foundational research that occasionally produces revolutionary breakthroughs and more often produces a deeper understanding of why certain things do not work. Both outcomes have value. The honest assessment of where warp drive research stands today is this: the Alcubierre solution is a mathematically valid solution to Einstein's field equations. It describes a geometry of space-time that, if it could be created, would allow faster-than-light travel without violating the local speed of light limit for the occupants. The fundamental obstacles are the requirement for exotic matter with negative energy density, which we do not know how to produce at any meaningful scale, and a set of additional physical problems that emerge when you look at the solution more carefully. Those additional problems are worth examining because they reveal just how deep and interconnected the challenges really are. One of the most serious issues with the Alcubierre drive was identified by physicists studying what happens inside the warp bubble from a quantum mechanical perspective. In 2012, a team of researchers including Stefano Finazzi, Stefano Liberati, and Carlos Barcelo published an analysis showing that quantum effects would cause the interior of a warp bubble to be flooded with high-energy radiation, similar in some ways to the Hawking radiation that Stephen Hawking predicted would be emitted by black holes. The mechanism is related to the same quantum vacuum effects we discussed with Unruh radiation in Part 3. The boundaries of the warp bubble, the regions where space-time transitions from flat inside the bubble to highly curved outside it, create horizons. And quantum field theory predicts that horizons produce radiation. The radiation builds up inside the bubble over time, and calculations suggest it would reach energies sufficient to destroy both the spacecraft and potentially the warp bubble itself. So even if you solved the exotic matter problem, even if you somehow obtained and engineered enough negative energy density to create the bubble, the quantum instability of the bubble interior might make it uninhabitable or self-destructing. There is also a profound problem with control. In the Alcubierre geometry, the region of space being manipulated to create the warp effect is outside the bubble, in the contracted and expanded space-time surrounding the craft. But the occupants inside the bubble are causally disconnected from that exterior region. Information cannot travel from inside the bubble to the bubble wall faster than light, which means the people inside cannot send signals to the exotic matter drive mechanisms outside to steer, stop, or modify the bubble. You cannot navigate your own warp bubble from the inside. It is like being sealed in a box that someone else is moving, except you have no way to communicate with the person moving it, and you cannot reach the controls. These are not small engineering details to be worked out later. They are fundamental physical constraints that emerge directly from the same relativity that makes the solution possible in the first place. And yet physicists keep working on it, keep refining it, keep asking whether there is a version of this idea that avoids the worst pitfalls, because the alternative, accepting that the stars are permanently, irrevocably out of reach for physical beings made of matter, is a conclusion that science is not yet prepared to declare final. In 2021, a paper by physicist Eric Lentz proposed a new class of warp solutions that he argued might work without requiring exotic matter at all, relying instead on what he called soliton solutions, self-reinforcing wave structures in space-time that could in principle be driven entirely by positive energy. The paper was published in the peer-reviewed journal Classical and Quantum Gravity, the same journal where Alcubierre's original work appeared. Critics pointed out significant remaining challenges with Lentz's approach, including the still enormous energy requirements, estimated at roughly equivalent to the mass energy of Jupiter converted to any form of fuel, positive or negative, and questions about stability. But the approach was taken seriously enough to generate genuine scientific discussion. Other researchers began extending and critiquing the framework. This is how theoretical physics works. Slowly, carefully, with enormous amounts of wrong turns, dead ends, and incremental refinements, and occasionally, not often, but occasionally, with a breakthrough that changes everything. We do not know which category warp drive research will ultimately fall into. That is not a comfortable answer, but it is the honest one. And I think honest uncertainty is far more interesting than false confidence in either direction. Now I want to step back from warp drives for a moment, because there is another proposed workaround for the light speed limit that is even more deeply rooted in mainstream physics. One that does not require exotic matter in the same way. One that is woven into the very equations of general relativity at a level even more fundamental than the Alcubierre metric, wormholes. The formal name is Einstein-Rosen bridges, named after Albert Einstein and his colleague Nathan Rosen, who first identified them as mathematical solutions to the field equations in 1935. A wormhole is a hypothetical tunnel through space-time, a shortcut that connects two distant regions of the universe, or potentially even two different universes, through a passage that could be far shorter than the distance between those regions through normal space. Imagine folding a piece of paper so that 2 points on opposite ends are brought close together, then poking a hole through both layers. A wormhole is the cosmic equivalent of that hole. Instead of traveling across the surface of the paper from one point to the other, a long journey, you step through the hole and emerge at your destination almost instantly. Einstein and Rosen's original solution described wormholes that were mathematically interesting but physically useless. They were unstable, collapsing faster than any signal or object could traverse them. In the 1980s, physicist Kip Thorne, who later shared the Nobel Prize in Physics in 2017 for his contributions to the detection of gravitational waves, was asked by his friend Carl Sagan to examine whether wormholes could theoretically be made traversable. Sagan was writing his novel Contact and wanted to use a wormhole as a plot device, and he wanted to know if it could be made scientifically defensible. Thorne took the question seriously and, together with his student Michael Morris, worked out the conditions under which a traversable wormhole could in principle exist. Their conclusion: it was mathematically possible. But like the Alcubierre drive, it required exotic matter with negative energy density to prop the throat of the wormhole open and prevent it from collapsing. Same fundamental requirement, same fundamental obstacle. The universe seems to be protecting its light speed limit with a consistent defense. Every time theorists find a mathematical route around it, exotic matter appears as the price of admission. Whether exotic matter at the required scales can ever exist in our universe is one of the open questions that sits at the boundary between theoretical physics and philosophy of science. We know the Casimir effect produces small amounts of negative energy. We know that quantum field theory in curved space-time, the framework that describes quantum mechanics in the presence of gravity, allows for regions of negative energy density in certain geometries. We do not know if these phenomena can be scaled up, engineered and sustained. Some physicists believe the answer is an eventual yes, that our understanding of quantum gravity, which remains incomplete, may one day reveal mechanisms for producing and manipulating exotic matter that we simply cannot see from our current theoretical vantage point. Others believe that when a fully consistent theory of quantum gravity is finally developed, a theory that unifies general relativity with quantum mechanics, which remains the single greatest unsolved problem in physics, it will introduce new constraints that close the wormhole and warp drive loopholes entirely. We do not know, and that unknowing is not a failure. It is an invitation. It is an invitation to keep building better telescopes, to keep colliding particles at higher energies, to keep developing the mathematical frameworks that might one day reveal a picture of reality clear enough to answer these questions definitively, to keep being the species that looks up at the stars and refuses to accept that questions are unanswerable simply because they are hard. Because here is what I want you to carry forward from this part of the story. From all of this, from warp bubbles and Einstein-Rosen bridges and exotic matter and quantum vacuums and Nobel Prizes and decades of careful, honest, difficult work, we are a species that has been doing science, real, systematic, evidence-based science, for only about 400 years. 4 centuries out of the 4.5 billion years our planet has existed. Out of the 13.8 billion years the universe has been here. We are extraordinarily, almost incomprehensibly young as a scientific civilization, and in those 400 years, we went from not knowing that other planets exist to landing machines on Mars. We went from not knowing that atoms are real to building devices that split them. We went from not knowing that the universe had a beginning to measuring the echo of that beginning, the cosmic microwave background radiation, the faint afterglow of the Big Bang itself, mapped in exquisite detail by missions like the Planck satellite, which operated from 2009 to 2013 and produced the most precise picture of the early universe ever made. We are just getting started. The question of whether human beings, or our descendants, or the machines we build, or some hybrid of both, will ever cross the vast distances between the stars is not answered yet. The physics we currently understand says it is extraordinarily difficult and perhaps impossible for matter to travel at or beyond the speed of light. But the physics we currently understand is also almost certainly incomplete. Every generation of scientists has inherited a framework that the next generation has refined, extended, or in some cases fundamentally revised. That is not a reason to be dismissive of current physics. Current physics is the most precisely tested body of knowledge in human history. It is a reason to be humble about the word impossible and curious about the edges where our understanding starts to blur. But let us not get lost in the theoretical possibilities to the point where we lose sight of the physical reality. Because we have spent this part of the video in the realm of equations and thought experiments, and I want to bring you back, sharply, viscerally back, to the human body, to your body, sitting in that spacecraft accelerating hard, because even setting aside all the exotic matter problems and quantum instabilities and navigation paradoxes, even if somehow none of those things existed, even in the most optimistic version of this thought experiment, your body itself has limits that physics cannot engineer away. Limits that come not from the laws of space-time but from the laws of biology, and those limits are where we are going next. We are going to talk about what acceleration itself, the physical act of getting to high speed regardless of the destination, does to human tissue, to the cardiovascular system, to the brain, about the G-forces involved, about what happens to your eyes, your lungs, your blood pressure, your consciousness, when you push a human body to the accelerations that interstellar travel requires. Because it turns out that even before the radiation gets you, even before the interstellar medium becomes a particle cannon, even before the blue-shifted starlight fries your hull, the simple act of speeding up might be enough to end the journey before it truly begins. Let us talk about your body not as an abstract collection of atoms, not as a philosophical concept or a passenger in a thought experiment. Your actual physical, biological body, the one you are living in right now, the one that evolved over hundreds of millions of years on the surface of a planet with a specific gravity, a specific atmosphere, a specific magnetic field, and a very specific set of physical demands that shaped every organ, every vessel, every cell you were made of, because that body, extraordinary as it is, capable as it is, resilient as it is, was not built for space. It was built for here, for Earth, for 1 g of gravitational acceleration, for atmospheric pressure of approximately 101,325 pascals, for radiation levels filtered through a magnetic field and an ozone layer that took billions of years to develop. Every system in your body assumes those conditions. And when you remove them, or worse, when you replace them with the conditions of a near-light speed interstellar journey, those systems begin to fail in ways that are medically documented, physiologically understood, and in some cases irreversible. We know this not from theory. We know this from data, from decades of human spaceflight, from the men and women who have lived aboard the International Space Station, some for over a year at a time, from the physiological studies run by NASA, by Roscosmos, by the European Space Agency, from blood draws and bone density scans and cognitive tests and eye exams conducted on returning astronauts, from the twin study, one of the most remarkable human biology experiments ever conducted, in which NASA astronaut Scott Kelly spent 340 consecutive days aboard the ISS, while his identical twin brother Mark Kelly remained on Earth, allowing researchers to compare biological changes between two people with identical genetics experiencing completely different physical environments. The data from that study and from decades of spaceflight research is humbling, and it is essential context for understanding what a journey to the stars would actually demand of the people inside the spacecraft. Let us start with the most immediate physical challenge of any high-speed journey: acceleration. To reach even a fraction of the speed of light in a reasonable amount of time, in years rather than centuries, A spacecraft would need to maintain sustained acceleration far beyond anything a human body can comfortably tolerate. Here is a useful reference point. Comfortable, sustained human acceleration, the kind you can endure for extended periods without physiological damage, is roughly 1 g, which makes sense because that is what we experience standing on Earth's surface. Our bodies are calibrated for it. Fighter pilots in high-performance aircraft can endure short bursts of up to 9 g with the help of specialized pressure suits that prevent blood from pooling in the lower body. Beyond that, even for seconds, the result is loss of consciousness, G-lock or G-induced loss of consciousness, as blood is forced away from the brain faster than the heart can compensate. The human body is remarkably fragile in this regard. 9 times your own body weight pressing down on every cell in your body simultaneously is, it turns out, not something evolution prepared you for. Now let us think about what sustained acceleration at 1 g, the most human-friendly acceleration conceivable, would mean for an interstellar journey. If you could maintain a constant acceleration of 1 g, pointing toward your destination for the first half of the journey, and then flipping and decelerating at 1 g for the second half, a trajectory that theoretical mission planners call a 1 g brachistochrone. The journey to Proxima Centauri, 4.2 light-years away, would take approximately 3.6 years of ship time. The passengers would feel normal Earth gravity the entire way, no weightlessness, no bone density loss, no cardiovascular deconditioning. That sounds almost manageable, right? Almost civilized. Except the energy required to maintain 1 g of acceleration for a crewed spacecraft over 4 light-years is once again a number that defies practical comprehension. For a spacecraft with a mass of even 1,000 tons, far less than the International Space Station, which masses approximately 420,000 kilograms, the fuel requirements at 1 g sustained acceleration exceed the total energy output of the Sun over several years, depending on your propulsion efficiency assumptions. Not the energy Earth receives from the Sun, the total energy the Sun radiates in all directions. For years, no known physics allows us to carry that much energy. No known physics allows us to convert it efficiently enough. The 1 g brachistochrone is beautiful in theory and essentially impossible in practice with any propulsion concept currently understood. So the realistic acceleration profiles for any near-future interstellar mission, the kind that physicists and engineers who think seriously about this actually discuss, involve much lower sustained accelerations. And that brings us back to the biology problem, because lower acceleration means longer journey times, and longer journey times mean more exposure to everything that space does to human physiology. Let us go through what we actually know from real mission data about what space does to the human body bone density. In the microgravity environment of the International Space Station, not the extreme of interstellar space, just the gentle weightlessness of low Earth orbit, astronauts lose approximately 1 to 2% of bone mineral density per month in load-bearing bones, the hip, the spine, the femur. Without the constant mechanical stress of gravity pulling down on the skeleton, the body interprets bone as metabolically expensive tissue that is no longer needed and begins reabsorbing it. 6 months in space produces bone density loss equivalent to decades of normal aging. Countermeasures exist. Astronauts on the ISS exercise for approximately 2 hours every single day using specialized resistance equipment, the Advanced Resistive Exercise Device, which uses vacuum cylinders to simulate weights in a weightless environment. This reduces bone loss but does not eliminate it. After long-duration missions, returning astronauts spend months in rehabilitation just to walk normally again. Scott Kelly, after his year in space, described the pain of readjusting to Earth's gravity as extraordinary. His skin, hypersensitized by months without normal contact pressure, hurt to the touch. His legs ached under their own weight. Muscle mass follows a similar trajectory. Without gravity to work against, muscles atrophy. The heart, which is a muscle, actually shrinks and reshapes in microgravity, becoming more spherical as it no longer needs to pump blood upward against gravity. Returning astronauts sometimes experience orthostatic intolerance, an inability to maintain adequate blood pressure when standing upright, because their cardiovascular system has partially forgotten how to fight gravity. These are not theoretical risks. These are documented, measured, recurring findings in almost every astronaut who has spent significant time in space. They are the reason human spaceflight beyond low Earth orbit, to the Moon, to Mars, certainly to the stars, requires solving problems in human physiology that we are still actively working on. Fluid shifts are another major issue. In microgravity, without the downward pull of gravity drawing bodily fluids toward the legs and lower body, fluid redistributes upward, toward the head. Astronauts often describe a persistent feeling of nasal congestion in space. Not from illness, but from fluid pressure in the upper body and head. Their faces puffy, their legs thin. This upward fluid shift has a more serious consequence. It increases intracranial pressure, the pressure inside the skull around the brain, and sustained elevated intracranial pressure has a documented effect on the optic nerve and the structure of the eye itself. This condition, called Spaceflight-Associated Neuroocular Syndrome, or SANS, has emerged as one of the most significant medical concerns in long-duration spaceflight. Studies of astronauts returning from long ISS missions have found that a significant proportion, some estimates suggest more than half of long-duration astronauts, show measurable changes to their vision. The optic nerve swells. The back of the eyeball flattens slightly, changing the focal length of the eye. Some astronauts return from 6-month missions needing prescription glasses for the first time in their lives. Others experience changes that persist for years after return to Earth. On a multi-year interstellar journey, even under constant acceleration that simulates gravity, the combined effects of the space environment on vision, bone, muscle, and cardiovascular function would require medical solutions that do not currently exist. We are not talking about minor inconveniences. We are talking about progressive, cumulative physiological degradation that could incapacitate crew members before they reach their destination. And then there is radiation, not the exotic, velocity-induced radiation we discussed in earlier parts, not the blue-shifted starlight becoming gamma rays, not the Unruh effect, not the interstellar medium transformed into a particle cannon, just ordinary space radiation, the kind that already exists in the solar system and beyond, the kind that astronauts are already exposed to at levels that concern physicians and mission planners every day. Earth's magnetic field and atmosphere shield us from most of the radiation that streams constantly through space. The Van Allen radiation belts, two donut-shaped regions of magnetically trapped charged particles surrounding Earth, are something spacecraft in low Earth orbit actually pass through on certain trajectories, and astronauts are carefully monitored for radiation exposure even in those relatively protected environments. Beyond the magnetosphere, radiation exposure increases dramatically. During the Apollo missions to the Moon, which lasted between 8 and 12 days, astronauts received radiation doses that, while within acceptable limits for those short durations, would be multiplied enormously over longer journeys. Several Apollo astronauts have reported seeing brief flashes of light with their eyes closed during the missions, a phenomenon now understood to be cosmic ray particles passing directly through the retina and triggering visual signals. Cosmic rays, particles accelerated to near-light speed by supernovae and other violent astrophysical events streaming through the galaxy in all directions. High-energy protons, helium nuclei, and heavier atomic nuclei traveling at 99.9% of the speed of light or more. They pass through spacecraft walls, they pass through human bodies, they can damage DNA directly, breaking chemical bonds, creating double strand breaks in the DNA helix that the cell's repair mechanisms may not correctly fix. Incorrectly repaired DNA damage is one of the primary mechanisms of radiation-induced cancer. NASA's current radiation limit for astronauts is set to keep the career radiation-induced cancer risk below 3% above background levels. For a mission to Mars lasting roughly 2 to 3 years round trip, current estimates suggest astronauts would receive a radiation dose equivalent to approximately 60% of that career limit just from the Mars mission alone, using current spacecraft shielding technology. A journey to the nearest star taking years or decades, even at aggressive speeds, would deliver doses many times higher. Heavy shielding can reduce exposure but not eliminate it, and heavy shielding means more mass. More mass means more energy to accelerate. More energy means more mass to carry as fuel. The engineering constraints loop back on themselves in a cycle that is familiar by now. Every solution to one problem creates or amplifies another. The cognitive and psychological dimensions of a multi-year interstellar journey deserve their own serious examination because they are as real and as challenging as any physical health concern, and in some ways harder to engineer around. Isolation and confinement are well-documented stressors in spaceflight. The ISS Crew Psychology Research Program has tracked crew dynamics, decision-making quality, sleep patterns, and emotional well-being across hundreds of missions. What it consistently finds is that long-duration crews experience predictable cycles of interpersonal friction, motivational decline, and cognitive performance degradation over time. The so-called third quarter phenomenon, a documented drop in morale and performance that occurs roughly 3/4 of the way through a long mission, has been observed in Antarctic winter-over cruise, submarine deployments, and spaceflight missions alike, on a journey measured in years or decades with no possibility of emergency return, with communication delays measured in years rather than minutes. The psychological demands on crew members would be unlike anything ever experienced in the history of human exploration. Even the most isolated explorer in human history, someone wintering over in Antarctica, someone on a 6-month ISS mission, has the knowledge that rescue is theoretically possible, that Earth is close, that they could, in extremis, come home. An interstellar crew would have none of that. Once you are 1 light-year from Earth, a radio message asking for help takes 1 year to arrive and another year for any response to return. For all practical purposes, you are beyond help. Every decision, medical, mechanical, navigational, interpersonal, falls entirely on the crew, and the crew is a small group of human beings, with all of human biology and human psychology sealed in a metal container for years, watching the stars shift almost imperceptibly as they creep across the incomprehensible distances between them. The selection, training, and psychological support of such a crew would be one of the most complex human challenges ever attempted. And we are not close to having solved it. I want to pause here because I am aware that this catalogue of challenges, the radiation, the bone loss, the vision damage, the psychology, the energy requirements, the exotic matter, the quantum instabilities, could start to feel like a closing door, like the universe is simply and definitively saying, no, I do not believe that is the right reading of this evidence. And I do not think the physicists and engineers who spend their careers on these problems believe it either. What this catalogue actually represents is a precise map of the distance between where we are and where we want to go. Not a wall, a map. And maps are useful. Maps tell you where the hard terrain is. They tell you which problems need to be solved before the journey can begin. They give you something to work toward. The history of human exploration is a history of maps like this, of obstacles that seemed insurmountable until they were not. The Atlantic Ocean was an insurmountable barrier until it was not. The sound barrier was an insurmountable barrier until it was not. The vacuum of space was an insurmountable barrier until Yuri Gagarin crossed it on the 12th of April 1961 and came back alive. Every barrier on that list was, at the time it was first confronted, genuinely daunting, genuinely uncertain, confronted by people who were told, sometimes by serious and respected voices, that it could not be done. And they did it anyway, not by ignoring the physics, by understanding it deeply enough to find the path through. That is the tradition we are part of. That is the story we are inside. And there is one more layer to this story that we have not yet touched. One that I think is the most philosophically profound of all the challenges we have discussed. One that goes beyond physics and biology and engineering and into the deepest question that any interstellar mission would have to confront, the question of time, not time dilation. We have covered that. But the simple, human, aching reality of what it means to leave, to travel for years or decades, to arrive somewhere and find that everyone you knew, everyone you loved, everyone who made you who you are, has aged or died in your absence. To return, if you return, to a world that has moved on without you. This is not a physics problem, it is a human problem, and in some ways it is the hardest one of all. Because the universe does not just challenge your body on this journey, it challenges your identity, your relationships, your sense of belonging to a place and a time and a people. It asks you whether the stars are worth the cost, not in fuel, not in engineering, but in the most personal currency any of us has, time, the unrepeatable, irreversible passage of your one life. That question has no scientific answer. It has only a human one, and different humans across the history of exploration have answered it differently. Some have said no, the cost is too high, the departure too permanent, the loss too great. Others have said yes, without hesitation, eyes on the horizon, hearts already beyond it, the interstellar traveler of the future. Whoever they are, whatever form they take, will have to answer it for themselves. But here is what the physics tells us, clearly and honestly. The journey, if it is ever made, will not be easy. It will not be safe. It will not be a weekend trip or a career milestone or an adventure with a comfortable return date. It will be the most demanding, most dangerous, most consequential thing any human or human-derived intelligence has ever attempted, and it will be worth asking whether it is worth it. Not because the answer is obviously no, but because the question deserves the full weight of honest consideration rather than the casual dismissal of difficulty that sometimes passes for optimism. The stars are real. The distances are real. The physics is real. And we are real, small, fragile, brilliant, restless, endlessly curious creatures on a pale blue dot, looking up and wondering. That wondering is not nothing. That wondering, in fact, might be everything. In part 6, we are going to take everything we have built, the physics, the biology, the philosophy, and look at what the most credible and serious proposals for actual interstellar missions actually look like. Not warp drives, not wormholes, real engineering proposals that real scientists have published in real journals and presented at real conferences. Proposals that try to work within the laws of physics rather than around them. Proposals like laser sail propulsion, like nuclear pulse drives, like the breakthrough Starshot initiative, backed by some of the most respected names in modern astrophysics, which aims to send a fleet of gram-scale spacecraft to Proxima Centauri within a generation, because the most inspiring part of this story is not the impossibility of what we cannot yet do. It is the breathtaking audacity of what we are already trying. Let us talk about what humanity is actually doing, not what we dream about, not what the equations permit in theory. Not what a civilization 1,000 years more advanced than ours might one day achieve. What we, Right now, today, with the technology and knowledge and resources we actually possess, are genuinely attempting in the direction of the stars, because the answer is more remarkable than most people realize. And it is happening quietly, methodically, with the kind of patient, rigorous determination that does not make headlines as often as it should, but represents something genuinely extraordinary about our species. We are right now in the early stages of planning and in some cases actively building the first real interstellar missions in human history, not crewed missions. Not yet. We are nowhere near solving the biological and energetic challenges we discussed in Part 5 for human travelers. But the principle, the act of sending something we built beyond the boundary of our solar system, aimed deliberately at another star, is not science fiction anymore. It is engineering, it is physics applied with intent, and some of the most respected scientists alive are working on it. Let us start with what has already left. 5 spacecraft have achieved escape velocity from our solar system. 5 human-made objects are, right now, traveling through interstellar space, beyond the heliopause, the boundary where the solar wind gives way to the interstellar medium, roughly about 100 astronomical units from the Sun, give or take depending on direction. 2 of them are the most famous, Voyager 1 and Voyager 2. Voyager 1 was launched on the 5th of September 1977, almost 50 years ago. It is currently the most distant human-made object ever built, sitting at roughly 23 billion kilometers from the Sun as of the time this script was written. That sounds like an enormous distance, and by any human scale, it is incomprehensible. 23 billion kilometers. But here is the perspective check that should stop you in your tracks. At that distance, Voyager 1 is approximately 0.00025 light-years from Earth. The nearest star, Proxima Centauri, is 4.2 light-years away. If Voyager 1 were aimed at Proxima Centauri, which it is not, it would take approximately 73,000 years to arrive at its current speed of roughly 61,000 kilometers per hour. 73,000 years. Modern humans have only existed for approximately 300,000 years. Agriculture was invented about 12,000 years ago. The entirety of recorded human history spans roughly 5,000 years, and the fastest spacecraft we have ever launched, traveling continuously for that entire span of recorded history, would not yet be 1/10 of the way to the nearest star. This is the scale of the problem. This is what makes the ambition of interstellar travel not just an engineering challenge, but a civilizational one. And yet, and this is the part I find genuinely electrifying, there are people alive today who are working on closing that gap. Not by a little, by orders of magnitude. The most ambitious and most credible near-term proposal for interstellar travel is called Breakthrough Starshot, announced in April of 2016 by Russian-Israeli entrepreneur and science philanthropist Yuri Milner with the public support of Stephen Hawking, who appeared at the announcement just over a year before his death, and with an advisory board that included Freeman Dyson, Anne Druyan, and Nobel Prize-winning astronomer Saul Perlmutter. Breakthrough Starshot is not a thought experiment. It is a funded research program with a specific defined objective. The goal is to send a fleet of tiny spacecraft, each one roughly the size and mass of a postage stamp, weighing about 1 gram, to the Alpha Centauri system, which includes Proxima Centauri, within the lifetime of people alive today. The target travel time is approximately 20 years. The proposed cruise speed is 20% of the speed of light, about 60 million kilometers per hour. Let those numbers sit for a moment. 20% of the speed of light. In 20 years of travel time to another star, the proposed propulsion system is not a rocket. It is a sail, a laser sail, the concept which physicists have been discussing seriously since at least the 1960s, when Robert Forward first explored it in detail, works like this. Each tiny spacecraft, called a starship, would be attached to an extraordinarily thin, lightweight reflective sail, perhaps a few meters across despite its microscopic thickness. From Earth, an array of ground-based lasers, collectively producing roughly 100 gigawatts of power, comparable to the output of 100 large nuclear power plants firing simultaneously, would focus their combined beam on the departing sail. The photon pressure from that focused laser beam would accelerate the tiny craft to 20% of light speed in a matter of minutes, from rest to 60 million kilometers per hour in a few minutes. The acceleration involved is approximately 30,000 g. No human being could survive that. No conventional spacecraft structure we currently build could survive that. The entire concept relies on the spacecraft being so small, so light, and so specifically engineered that the forces involved, while enormous in absolute terms, do not destroy the sail or the electronics attached to it. Each starship would carry a camera, navigation sensors, communication equipment, and enough computing power to send data back to Earth. The round-trip communication time for a signal from Alpha Centauri is approximately 8.4 years, so the earliest we could receive imagery from another star system, if everything worked, if the technology was ready tomorrow, if the mission launched soon, is somewhere around 30 years from the launch date. 20 years of travel, 8 years for the signal to return, within a human lifetime, potentially within the lifetime of the scientists currently working on it. Is breakthrough Starshot technically feasible with current technology? The honest answer is, not quite yet. But the obstacles are engineering obstacles, not physics obstacles. Every component of the concept is consistent with known physics. The challenges are real but specific, and specific challenges can be worked. The laser array is perhaps the most daunting. 100 gigawatts of phased, coherent, precisely steerable laser power does not exist. Building it would require a global-scale engineering effort, international cooperation, and investment on a scale comparable to CERN or larger. The estimated cost in current dollars runs to the tens of billions, significant, but not incomprehensible for a multi-decade program with international backing. The sail material is another frontier. It needs to reflect the laser with near-perfect efficiency. Absorbing even a fraction of a percent of 100 gigawatts would vaporize it instantly, while being thin enough and light enough to be accelerated to 20% of light speed. Current materials science is approaching, but has not yet reached the required specifications. Graphene-based films and other two-dimensional materials are being actively investigated. The physics permits it. The manufacturing does not quite get there yet. The starship electronics need to survive both the brutal acceleration phase and then approximately 20 years of exposure to the interstellar radiation environment. With no repair missions possible, with no ground control to diagnose failures in real time, everything has to work autonomously for 2 decades in conditions more hostile than anything we have previously engineered for. These are hard problems. They are also, by the assessment of serious engineers and physicists who have examined them in detail, solvable problems, not tomorrow, but within decades with sustained effort and investment. Breakthrough Starshot is not a fantasy. It is an engineering program operating at the edge of current capability, with a clear roadmap toward a defined objective. It is the most concrete step our civilization has ever taken toward reaching another star. But laser sails are not the only serious proposal on the table. Let us talk about some others, because the breadth of serious thinking being applied to this problem is itself remarkable and worth knowing about. Nuclear pulse propulsion is a concept that has been studied seriously since the late 1950s, when a remarkable and somewhat surreal program called Project Orion explored the possibility of propelling a large spacecraft by detonating nuclear bombs behind it in rapid succession. The expanding plasma from each detonation would push against a large pusher plate at the rear of the spacecraft, producing thrust. The physics of Orion was analyzed by serious scientists including Freeman Dyson, one of the most brilliant theoretical physicists of the 20th century, who calculated that a nuclear pulse ship could in principle reach speeds of several % of the speed of light with conventional nuclear fission explosives and potentially higher fractions of light speed with thermonuclear fusion devices. The concept was studied seriously enough to build and test small chemical explosive models that demonstrated the basic pusher plate principle worked. Project Orion was eventually cancelled, not because the physics failed, but because of the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space. The political and environmental concerns that surrounded nuclear weapons testing in the 1960s made continued development of a nuclear bomb-propelled spacecraft politically impossible, regardless of its scientific merit. But the physics remains valid, and more refined descendants of the concept, including a British Interplanetary Society study called Project Daedalus in the 1970s, which proposed using inertial confinement fusion rather than fission bombs, and its successor Project Icarus, which updated the analysis in the 2010s, have consistently found that fusion pulse propulsion could in principle achieve speeds of 10 to 12% of the speed of light, enough to reach Proxima Centauri in roughly 40 to 50 years. Project Daedalus was a serious, detailed, years-long study by real engineers and physicists, not a casual thought experiment. They designed an actual spacecraft, 2 stages, roughly 50,000 tons at launch, carrying 18,000 tons of fusion fuel in the form of frozen pellets of deuterium and helium-3. They calculated the acceleration profile, the cruise phase, the deceleration options, or rather, the lack of them, since Daedalus was designed as a flyby mission with no braking system, because the mass required to decelerate would have made the spacecraft impractically large. Helium-3, the proposed fusion fuel, is extraordinarily rare on Earth, but exists in significant quantities in the regolith of the Moon and in the atmospheres of the gas giant planets. Harvesting it at the scale required for a Daedalus-class mission would itself be a major civilizational undertaking. But again, an engineering challenge, not a physics impossibility. There is another propulsion concept that deserves mention because it appears with some regularity in serious interstellar propulsion literature and has a particularly elegant underlying physics: the magnetic sail, or MagSail, proposed by physicist Robert Zubrin, who is perhaps better known as one of the most passionate and detailed advocates for human Mars exploration, and Dana Andrews in 1991. The magnetic sail concept involves generating a large magnetic field around a spacecraft using a superconducting loop of wire. This magnetic field would interact with the solar wind, the constant stream of charged particles flowing outward from the Sun, and with the interstellar medium, creating a form of drag-free sailing on particle streams rather than light. In the interstellar medium, a magsail could be used not to accelerate but to decelerate, to slow down a spacecraft arriving at a destination star without carrying any fuel for braking. This is important because deceleration is one of the thorniest problems in any interstellar mission design. Every gram of fuel you bring for slowing down at the destination is a gram you have to accelerate to cruise speed first, multiplying your fuel requirements enormously. If the interstellar medium itself can serve as a brake, the mission architecture becomes significantly more achievable. Zubrin's original calculations suggested that a magsail could reduce a spacecraft's velocity from a significant fraction of light speed to manageable orbital velocities over a journey through the interstellar medium. The concept requires superconducting wire that can maintain its properties in the radiation environment of deep space, and the magnetic field needs to be enormous, potentially hundreds of kilometers in diameter, to interact with the diffuse interstellar plasma effectively. But the physics is sound, and the engineering, while challenging, is not fundamentally beyond the direction current materials science is heading. Let us also talk briefly about antimatter propulsion, because no survey of serious interstellar propulsion concepts would be complete without it, and because the physics of antimatter is so extraordinary that it deserves at least a moment of your attention. Antimatter is real. It is not science fiction. Every major particle physics laboratory in the world produces it routinely. When particles are accelerated and collide at high energies, antimatter particles are created as a natural byproduct of the collision. Positrons, the antimatter equivalent of electrons, are produced in such quantities that they are used medically in PET scans, positron emission tomography, which is one of the most powerful diagnostic imaging tools in modern medicine. Every PET scanner in every hospital in the world is using antimatter. When a particle of matter meets its antimatter counterpart, they annihilate each other completely. Every bit of their combined mass is converted into pure energy, into gamma rays, with 100% efficiency. Compare that to nuclear fission, which converts less than 1% of mass to energy, or nuclear fusion, which converts less than 1% as well. Antimatter annihilation is the most energy-dense reaction permitted by known physics. Gram for gram, it releases approximately 10 billion times more energy than chemical combustion and roughly 100 times more energy than nuclear fission. For an interstellar spacecraft, even a few tens of grams of antimatter, if it could be used as propellant, would provide energies sufficient to accelerate a significant payload to meaningful fractions of the speed of light. The problem is production and storage. Currently, the world's most productive antimatter facility, CERN's antiproton decelerator, produces antiprotons at a rate of roughly several tens of millions per second. That sounds like a lot. It is not. Several tens of millions of antiprotons has a combined mass of approximately 10 to the power of negative 17 kilograms, a fraction of a billionth of a gram. At current production rates, it would take billions of years to produce a single gram of antimatter. Production efficiency is improving. Researchers have explored concepts for antimatter harvesting from natural sources, from the Van Allen radiation belts, where some antimatter is naturally produced by cosmic ray interactions with the upper atmosphere. But the quantities involved, even optimistically, remain far below what interstellar propulsion would require. Antimatter propulsion is physically the most elegant solution to the interstellar energy problem. It is also, at our current level of technological development, the most practically distant. But it is being studied, and the direction of travel in particle physics and materials science suggests that production efficiency and storage technology will improve, even if the timescale for reaching mission-relevant quantities remains extremely uncertain. What strikes me most about all of these proposals, laser sails, nuclear pulse drives, magnetic sails, antimatter engines, is not any one of them individually. It is the collective picture they paint when you step back and look at them together. There are serious human beings with real credentials at real institutions, spending real portions of their lives working on how to send something, eventually someone, to another star, not as a hobby, not as a fantasy, as a scientific and engineering program with defined objectives, published methodologies, peer-reviewed analyses, and iterative improvement over decades. The Tau Zero Foundation, founded by Mark Millis, a former NASA researcher who led the Breakthrough Propulsion Physics program at the Glenn Research Center, exists specifically to advance interstellar flight research and connect the global community of scientists and engineers working on these problems. The Initiative for Interstellar Studies, based in the United Kingdom, publishes a journal, runs conferences, and coordinates research across multiple propulsion and mission architecture concepts. The British Interplanetary Society, one of the oldest space advocacy organisations in the world, founded in 1933, before the first liquid-fueled rockets had even flown, has a continuous tradition of serious interstellar mission design, stretching back to Project Daedalus. These organisations and the people within them are part of a tradition, a long, patient, occasionally frustrated, but never defeated tradition of human beings looking at impossible distances and asking, not if, when, and how. And here is where I want to bring this back to you, to the personal, to the human dimension of everything we have been discussing across these 6 parts. We started this video with a thought experiment, you in a spacecraft, engines igniting, trying to reach the speed of light. We have spent these 6 parts dismantling that dream systematically, showing you the radiation, the mass increase, the exotic matter requirements, the biological deterioration, the psychological demands, the energy mathematics that spiral toward infinity. But dismantling a naive dream is not the same as destroying a real one. The naive dream was always going to be wrong. The naive dream assumed the universe was a blank canvas on which we could simply paint whatever we wanted. The real dream, the dream being pursued right now by real people with real science, knows the canvas has structure, has rules, has constraints, and it works within those constraints rather than pretending they do not exist. That is what science is. Not the denial of limits, the precise, honest, patient mapping of limits, so that we know exactly which limits are permanent and which ones are simply waiting for us to be clever enough to work around them. The speed of light appears to be permanent. The biology of human spaceflight is not. It is being actively addressed. The energy requirements of known propulsion systems are not permanent. They are being actively reduced through new concepts. The distance to the stars is not changing, but our ability to cross it slowly, tentatively, through incremental steps of understanding and engineering appears to be growing. That growth, that slow, generational, civilizational reaching toward the stars, is going to require something that no spacecraft can carry and no laser can provide. It is going to require a quality of human spirit that I think is worth naming directly, because it is easy to take for granted and easy to forget when the numbers get discouraging. It is going to require the willingness to work on things whose completion you will never see. The scientists who designed Project Daedalus in the 1970s knew perfectly well that they were not going to live to see a fusion pulse spacecraft launched toward the stars. The researchers working on breakthrough Starshot today know that even in the most optimistic scenario, the data from a Starship flyby of Alpha Centauri will not arrive until they are old, if they are still alive at all. The theorists refining warp drive mathematics and wormhole geometries are working on solutions to problems that may not be experimentally testable for generations. They do it anyway, because the work matters even when the reward is not personal, because knowledge compounds across generations, because every paper written, every constraint identified, every dead end mapped, narrows the problem for whoever comes next. This is the deepest form of optimism I know, not the shallow optimism that says everything will work out fine, but the earned, eyes-open optimism of people who understand exactly how hard the problem is and choose to work on it anyway, not because success is guaranteed, but because the attempt is worth making. We are made of the same atoms that were forged in stellar cores billions of years ago. We are literally built from stardust, from the remnants of stars that lived and died before our sun was born. And now, 4.5 billion years after that dust coalesced into a planet, and about 300,000 years after something on that planet became curious enough to look up at the stars it came from. We are trying to go back. That is not just science. That is the universe becoming aware of itself and trying to explore its own vastness. And I do not know about you, but I find that almost unbearably beautiful. Let us talk about the edge of everything, not the edge of our solar system, not the edge of our galaxy, the edge of the observable universe itself. The boundary beyond which no light has ever reached us, no signal has ever arrived, no information of any kind has ever crossed. The place where the cosmos, as far as we are concerned, simply stops. And I want to be precise about something right from the beginning of this conversation, because it is one of the most commonly misunderstood ideas in all of cosmology, and getting it wrong means missing something genuinely profound about the nature of reality. The observable universe is not the whole universe. It is not even necessarily most of the universe. It is simply the portion of the universe from which light has had enough time, in the 13.8 billion years since the Big Bang, to travel far enough to reach us. It is a sphere of knowability centered on Earth, not because we are special or central, but because we are here, and light travels at a finite speed, and time has a beginning. Beyond the edge of that sphere, there is almost certainly more universe, possibly vastly more, possibly infinitely more. We do not know. We cannot know. Not because our telescopes are not powerful enough, but because the light from those regions has not reached us yet, and in many cases will never reach us because the space between us and them is expanding faster than the light can cross it. That last sentence deserves to be read twice. The space between us and the most distant regions of the universe is expanding faster than light. Not because anything is moving through space faster than light, that would violate relativity, but because space itself is expanding, and when you add up the expansion across the vast distances involved, the rate at which distant regions recede from us exceeds the speed of light. This is not a violation of physics. It is a consequence of it. To understand this properly, we need to go back to something we touched on briefly in Part 4. The expansion of the universe. In 1929, Edwin Hubble published observations showing that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it appears to be receding. This relationship, known as Hubble's law, was the first observational evidence that the universe is expanding. Not expanding into anything, not expanding from a central point, just expanding every region of space, growing slightly larger over time, so that the distance between any two points that are not gravitationally bound to each other increases continuously. The rate of that expansion is described by a number called the Hubble constant, denoted h0. Its precise value has been one of the most actively debated measurements in modern cosmology, partly because different measurement methods give slightly different answers. A discrepancy called the Hubble tension that is currently one of the most significant unresolved puzzles in the field. But the approximate value is around 67 to 73 kilometers per second per megaparsec. What that means in practical terms is that for every megaparsec of distance between us and a galaxy, 1 megaparsec being approximately 3.26 million light-years, that galaxy is receding from us at an additional 67 to 73 kilometers per second due to cosmic expansion alone. At small distances, this recession velocity is tiny compared to the speed of light. A galaxy 1 megaparsec away recedes at roughly 70 kilometers per second. The speed of light is 299,792 kilometers per second. No problem, but as you go further, the recession velocity adds up. At a distance of about 14 billion light-years, a distance well within what our telescopes can observe, galaxies are receding from us at exactly the speed of light. beyond that distance, they recede faster than light, and light from those galaxies, trying to reach us across that expanding gulf, is essentially running on a treadmill, making progress locally through space, but being carried backward by the expansion faster than it can advance. Those galaxies are observable, just barely, because the light we see from them was emitted long ago, when the universe was smaller and the distances were shorter, but they are no longer reachable, not by us, not ever. The expansion has sealed them off, as surely as if they had crossed the event horizon of a black hole. The boundary at which recession velocity equals the speed of light is called the Hubble radius, and it currently sits at approximately 14 billion light-years from Earth. But the actual edge of the observable universe, the cosmic particle horizon, sits further out at about 46 billion light-years. How can the observable universe be 46 billion light-years across if the universe is only 13.8 billion years old and light only travels at a finite speed? Because the universe has been expanding the entire time that light has been traveling. The light we are receiving right now from the most distant observable sources was emitted when those sources were much closer to us than they are today. In the 13.8 billion years since that light was emitted, the universe has expanded enormously, carrying those sources to their current distances of about 46 billion light-years. We are seeing those objects as they were in a much smaller, younger universe, not as they are now, the most ancient light we can detect, the cosmic microwave background radiation, the faint thermal glow left over from the hot plasma of the early universe, emitted approximately 380,000 years after the Big Bang, comes from a surface that was then about 42 million light-years away from us. Today, the region of space that emitted that radiation is approximately 45 billion light-years away. We are seeing it as it was, separated from us by 42 million light-years, but it now sits at 45 billion light-years distance, carried there by 13.8 billion years of cosmic expansion. The Planck satellite, a European Space Agency mission that operated from 2009 to 2013, mapped this cosmic microwave background in extraordinary detail, producing a picture of the universe as it looked less than 400,000 years after its birth, when it was a glowing, nearly uniform fog of hot plasma. The temperature variations in that map, tiny fluctuations of about 1 part in 100,000, are the seeds of everything that exists today. Every galaxy, every star, every planet, every ocean, every living thing, all of it grew from those quantum fluctuations in the infant universe, amplified by gravity over billions of years into the cosmic web of structure we see today. That image, the Planck map of the cosmic microwave background, is the oldest picture ever taken, a baby photo of the universe, captured in microwave light by a spacecraft orbiting a point in space called the second Lagrange point, 1.5 million kilometers from Earth. We did that. We built that spacecraft. We launched it. We received its data. We processed it. We read the oldest light in the universe. Let that sit for a moment now. Back to the edge, the observable universe has a radius of approximately 46 billion light-years. Everything within that sphere is, at least in principle, observable. We could receive light or other signals from it, given enough time and a powerful enough telescope. Everything outside that sphere is not just unseen. It is unseeable, permanently beyond our cosmic horizon. But here is the part that genuinely unsettles cosmologists when they sit with it long enough. The observable universe is not the whole universe, and the whole universe may be incomprehensibly larger than the observable part. During the period of extremely rapid expansion in the very early universe called inflation, a theory developed primarily by physicist Alan Guth in 1980 and subsequently refined by André Linde, Paul Steinhardt, and others, The universe is thought to have expanded by a factor of at least 10 to the power of 26 in a tiny fraction of a second. Some versions of inflationary theory predict expansion by factors far larger than that. Effectively, inflation took a region of space far smaller than an atomic nucleus and stretched it to a size enormously larger than what we can currently observe. If inflation happened as the mathematics suggests, then the total size of the universe, all of it, not just the observable part, could be millions, billions, or even infinitely many times larger than our cosmic horizon. Our observable bubble, 46 billion light-years in radius, would be a tiny, almost negligible fraction of the whole, like a single grain of sand compared to all the beaches on Earth. Or smaller, far smaller. We do not know what exists in those regions beyond our horizon. It is the ultimate epistemic boundary, not a boundary of our telescopes or our technology, a boundary of causality itself. No signal, no light, no information of any kind can reach us from beyond that horizon, not because we have not waited long enough, but because the expansion of the universe is accelerating, driven by dark energy, carrying those regions away from us faster and faster with every passing second. In fact, due to the accelerating expansion, the observable universe is actually shrinking over cosmic time. Galaxies that are currently just barely within our observable horizon will eventually recede beyond it entirely. Their light will redshift to zero energy, their signals will fade to nothing, and they will be forever lost to us. Not destroyed, simply gone beyond the reach of any communication. In the far future, tens of billions of years from now, an observer in our galaxy would look out at a much emptier sky. Most of the galaxies visible today would have receded beyond the horizon. The cosmic microwave background would have redshifted to wavelengths too long to detect. The evidence for the Big Bang, for cosmic expansion, for the existence of the wider universe, all of it would have faded to undetectable levels. A civilization arising then, in that future, would look at the sky and see only their own local group of gravitationally bound galaxies. They would have no evidence of the wider cosmos. They might conclude, reasonably, that what they see is all there is. They would be wrong, but they would have no way of knowing that. We are fortunate. We live at a time when the evidence of the universe's history and scale is still visible, when the light from the early universe still reaches us, when the expansion is measurable, when the structure of the cosmos is still legible in the sky above us. Future civilizations will not have this window. We are living in the golden age of cosmological observation, and most of us have no idea. Now let us bring this back to the light speed limit. Because the cosmic horizon and the expansion of the universe are not just abstract cosmological facts. They are directly connected to the question this video has been exploring from the beginning. If you cannot travel faster than light, if the speed of light is the absolute, inviolable cosmic speed limit, then the accelerating expansion of the universe means that most of the universe is not just far away. It is permanently, irrevocably unreachable, not difficult to reach, not reachable given enough time, unreachable, forever. The galaxies currently receding from us faster than light. Everything beyond that Hubble radius of 14 billion light-years cannot be reached by any physical traveler, no matter how advanced their technology, as long as the expansion continues to accelerate. You could travel for the entire remaining lifetime of the universe, trillions upon trillions of years, and you would never close the gap. The distance would keep growing faster than you could travel. This is, philosophically, one of the most vertiginous facts in science. The universe we inhabit contains, by most estimates, at least 2 trillion galaxies within the observable volume. 2 trillion. The Hubble Space Telescope's ultra-deep field images, those famous long-exposure photographs of tiny patches of seemingly empty sky, revealed thousands of galaxies in a region of sky smaller than a grain of sand held at arm's length. Each of those galaxies containing hundreds of billions to trillions of stars, each of those stars potentially orbited by planets, each of those planets potentially harboring conditions for chemistry, for complexity, for life, and nearly all of it is already beyond our reach. Not because we have not tried, because the universe is expanding too fast and has been for too long for the light from those regions to ever catch up to us again. We are cosmically isolated. Not in our solar system we can reach that. Not in our galaxy in principle. With the right technology and the right timescales, a sufficiently advanced civilization could traverse the Milky Way. Not even in our local group of galaxies. The gravitational binding of the local group, which includes the Milky Way, Andromeda, and several dozen smaller satellite galaxies, is strong enough to hold them together against the expansion indefinitely. They are ours in a cosmic sense. But beyond the local group, the accelerating expansion is pulling everything else away. The Virgo cluster, the Coma cluster, the great filaments and walls of the cosmic web stretching across hundreds of millions of light years. They are going, slowly, invisibly, but inexorably. There is a concept in cosmology called the cosmic event horizon, not to be confused with the particle horizon we discussed earlier. The cosmic event horizon is the boundary beyond which events happening right now will never be able to send a signal that reaches us. It currently sits at about 16 billion light-years from Earth. Any galaxy beyond that distance, any supernova exploding, any civilization rising, any signal being sent right now, will never reach us. The expansion of space between here and there will outpace any signal they send before that signal can arrive. They are beyond our cosmic event horizon, permanently, and we are beyond theirs. If there are civilizations out there, scattered across the hundreds of billions of galaxies beyond our cosmic horizon, they cannot reach us, they cannot signal us, they cannot know we exist, and we cannot know they exist, not because of distance in the conventional sense, because of the fundamental architecture of an expanding universe governed by a finite speed of light and an accelerating expansion driven by dark energy. We may never be alone in the universe in any philosophical sense, but we may be permanently isolated from most of it in any practical sense. Dark energy deserves more than a passing mention here, because it is one of the most profound mysteries in modern physics, and its role in the story of the cosmic horizon is central. In 1998, two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were using Type Ia supernovae as standard candles to measure the expansion rate of the universe across cosmic time. Type Ia supernovae are explosions of a very specific and consistent type, producing a known intrinsic brightness which allows astronomers to calculate their distance precisely by comparing that intrinsic brightness to their apparent brightness in the sky. The dimmer they appear, the further away they are. The teams expected to find that the expansion of the universe was slowing down. Gravity, after all, pulls matter together. The Big Bang gave everything an initial outward velocity, but gravity should be gradually decelerating the expansion over time. That was the expectation. What they found instead stopped the astronomical community in its tracks. The distant supernovae were dimmer than expected, not brighter, dimmer, which meant they were further away than the decelerating expansion model predicted. The universe was not slowing down, it was speeding up. The expansion of the universe is accelerating. Something is driving space apart with increasing force, overcoming gravity on the largest scales. Something that permeates all of space, that has no apparent source in any known matter or energy field, that appears to be a property of space itself, a constant energy density of the vacuum that pushes outward as the universe expands. We call it dark energy. We do not know what it is. We know it makes up approximately 68% of the total energy content of the universe. We know it is causing the expansion to accelerate. We know it is shrinking our cosmic horizon over time. We know it is the reason most of the universe is already permanently beyond our reach. Beyond that, we are deeply, honestly, unsettlingly uncertain. The cosmological constant, a term Einstein himself introduced into his field equations in 1917, then removed, calling it his greatest blunder before it was reinstated by the supernova observations, is the simplest mathematical description of dark energy. But we do not know whether it is truly constant over time, whether it varies across space, whether it is a fundamental property of space-time or a field that evolves. These are open questions, active research questions, questions being pursued with instruments like the Dark Energy Spectroscopic Instrument, currently operating at the Kitt Peak National Observatory in Arizona, and the Euclid satellite launched by the European Space Agency in 2023, which is mapping the three-dimensional distribution of galaxies across billions of light-years to trace the history of cosmic expansion with unprecedented precision. We are trying to understand what is accelerating the expansion of our universe. We do not know yet, but we are asking the question with better tools than ever before. And that is exactly where science should be. I want to take a moment here, in the middle of all this cosmic scale, all this talk of horizons and dark energy, and the permanent inaccessibility of most of existence, to bring it back to something intimate. You are a collection of atoms that have existed in various forms for billions of years. The carbon in your body was forged in the core of a star that died before our sun was born. The iron in your blood was scattered across space by a supernova explosion. The water you drank this morning contains hydrogen atoms that have been part of the universe since the first few minutes after the Big Bang, when the cosmos was hot enough to fuse protons into the nuclei of the lightest elements. You are not separate from the universe you are trying to understand. You are part of it, literally constructed from it. And the curiosity you feel, the pull toward understanding, the ache of not knowing, the wonder at the scale of it all. Is the universe experiencing itself through the particular arrangement of atoms that constitutes you? The cosmic horizon that limits what we can see and reach does not diminish us. It contextualizes us. It reminds us that we are embedded in something far larger than ourselves, something that was here long before us and will be here long after us. Something that does not need us to observe it to be real, but that becomes, in some important sense, more fully itself when we do. There is a passage from the astronomer Carl Sagan that I keep returning to. He wrote, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." That sentence is not poetry dressed as science. It is science expressed as poetry. The atoms in your body are genuinely, literally, chemically the residue of stellar nucleosynthesis. And the awareness you have of that fact, the ability to trace the lineage of those atoms back through supernovae and stellar cores and the Big Bang itself, is something that, as far as we know, is extraordinarily rare in the universe. Perhaps unique. You are the universe looking at its own edge, wondering what is beyond it, unable to cross it but unable to stop asking. That is not a tragedy. That is the most remarkable thing about being alive. If you are still watching, you're exactly who we make these videos for. Don't forget to subscribe and give this a like. Every day we go further, ask harder, and come back with the kind of understanding that actually shifts something in you. Let us talk about the silence. Because in all of this, in everything we have covered across 7 parts of this journey, there is one fact that sits quietly at the center of it all, like a stone dropped into still water, sending ripples through every assumption we make about the cosmos and our place in it. We have never heard from anyone else, not a signal, not a pattern, not a repeating pulse from a distant star that turned out to be artificial rather than natural, not a narrowband radio transmission at the hydrogen line frequency, the wavelength of 21 centimeters, the most abundant element in the universe, the frequency that physicists in the 1950s identified as the most logical channel for interstellar communication. Not a laser pulse, not an unexplained engineering structure orbiting a star, not a confirmed anomaly in any dataset from any telescope that has held up under scrutiny as evidence of intelligence beyond our own. In over 60 years of systematic searching, since Frank Drake pointed a radio telescope at two nearby sun-like stars in 1960 and listened, we have detected nothing that could be confidently attributed to a technological civilization elsewhere in the universe. The universe is vast, it is ancient, it is filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, many of them orbited by planets, many of those planets sitting in the temperature range where liquid water can exist on their surfaces. The conditions for the chemistry of life appear to be widespread. The time available for intelligence to arise elsewhere has been enormous. The universe has been around for 13.8 billion years, and stars capable of supporting life-bearing planets have existed for nearly that entire span, and yet silence. This is the Fermi paradox, named after the physicist Enrico Fermi, who allegedly asked the question at a lunch conversation at Los Alamos in 1950. Though the historical record of exactly what he said is somewhat uncertain, the paradox is simply stated: given the apparent abundance of conditions suitable for life in the universe, where is everybody? Why is the cosmos quiet? Let us be precise about what makes this a genuine paradox and not just a shrug of ignorance. The argument for why we should expect to hear from someone, somewhere, rests on a few straightforward observations. First, the Milky Way galaxy alone contains somewhere between 200 and 400 billion stars. Second, we now know, from the Kepler Space Telescope's planet-hunting mission, which operated from 2009 to 2018 and confirmed the existence of over 2,600 exoplanets, that planets are extraordinarily common. Most stars have them. Many have multiple. A significant fraction appear to have rocky planets in the habitable zone, the orbital range where liquid water could exist on the surface. The Kepler mission fundamentally changed our picture of the galaxy. Before Kepler, we knew planets existed around other stars in principle. After Kepler, we understood that the galaxy is essentially carpeted with them. Estimates based on Kepler's data suggest there could be tens of billions of Earth-sized planets in the habitable zones of sun-like stars in the Milky Way alone. Tens of billions in one galaxy out of 2 trillion. Third, life on Earth arose remarkably quickly after the planet formed. Earth is approximately 4.5 billion years old. The oldest confirmed evidence of microbial life dates to approximately 3.5 billion years ago, with some chemical signatures suggesting life may have appeared even earlier, possibly within a few 100 million years of Earth's formation. By cosmic standards, life appeared here almost immediately after conditions permitted it. This suggests, though does not prove, that the chemistry of life may not require extraordinary conditions or extraordinary luck. It may be a relatively robust process that arises whenever the right ingredients are present in the right environment for long enough. Fourth, intelligence and technology, once they arise, appear capable of spreading rapidly on cosmic timescales. Even at the modest speeds of current human technology, far below the speed of light, a sufficiently motivated civilization could theoretically colonize the entire Milky Way galaxy within a few million years. That is a long time by human standards. By galactic standards, it is an eye blink. The Milky Way is approximately 10 billion years old. A civilization that arose 5 billion years ago and expanded at even a tiny fraction of the speed of light, would have had time to reach every corner of the galaxy many times over. So where are they? Where is the evidence of their passage? Their engineering? Their signals? Their presence? The silence is not nothing. The silence is data, and it is deeply puzzling data. The proposed resolutions to the Fermi paradox span an enormous range from the optimistic to the sobering to the genuinely terrifying. Let us go through some of the most seriously considered ones, because each of them says something different and important about the universe and about us. The first and most reassuring resolution is simply that we have not looked hard enough, long enough, or in the right ways. The SETI Institute, the Search for Extraterrestrial Intelligence, a non-profit research organization based in California that has been conducting systematic searches of the radio spectrum and beyond for decades, has surveyed only a tiny fraction of the parameter space of possible signals. Radio frequencies, optical lasers, the specific stars and sky regions examined, the duration of observations, all of these represent a search that, however dedicated, covers an almost negligibly small portion of the full range of possible signals from the full range of possible stars across the full range of possible times. Astronomer Jill Tarter, former director of the SETI Institute and one of the pioneers of systematic signal searching, offered an analogy that puts this in perspective. She described our SETI searches so far as equivalent to searching for fish in the Earth's oceans by filling a drinking glass with ocean water, looking in the glass, finding no fish, and concluding the ocean contains no fish. The sample is that inadequate relative to the search space. This is a reasonable and important point. We should not overinterpret the silence as definitive evidence of absence. Absence of evidence is not evidence of absence, particularly when the evidence we have collected is so sparse relative to the space we need to search. But there is a counter-argument, and it is a serious one. Even without detecting a radio signal, which requires a directed transmission or a lucky intercept, we might expect to see other signatures of technological civilization, engineering on a large scale, stars with anomalous energy signatures, megastructures, the waste heat from a sufficiently advanced industrial civilization, and on all of those fronts, too, the silence is striking. A second class of resolution suggests that life is rare, perhaps extraordinarily rare. Perhaps we are, in some meaningful sense, alone or nearly alone in the observable universe. This position is associated with what biologist Peter Ward and astronomer Joe Kirschvink call the rare Earth hypothesis, developed in their book of the same name, published in 2000. The argument is that Earth is not a typical planet. It is an extraordinarily specific combination of conditions: the right distance from the right kind of star, the right size, the right composition, a large moon stabilizing the axial tilt, a giant planet like Jupiter deflecting incoming asteroids, a liquid iron core generating a protective magnetic field, plate tectonics recycling carbon and regulating climate over billions of years. That may be deeply uncommon even in a universe carpeted with planets. On this view, simple microbial life might be widespread. The chemistry is robust, and the conditions for basic metabolism may exist in many places. In subsurface oceans on moons like Europa and Enceladus, for example, which are among the most exciting targets in the search for life within our own solar system. But complex, multicellular life, animals, nervous systems, intelligence, technology, might require such a specific and improbable set of circumstances that our galaxy contains very few examples, possibly only one. The rare Earth hypothesis is not widely accepted as the definitive answer, but it is taken seriously, and recent advances in astrobiology have added nuance to the picture. We now understand that the emergence of complex eukaryotic cells, the cell type that all complex life on Earth is built from, appears to have happened exactly once in the 4 billion-year history of life on this planet. a single endosymbiotic event, probably around 2 billion years ago, in which one bacterium engulfed another and they merged into a single more complex cell. That cell was the ancestor of every plant, animal, fungus, and protist that has ever existed, a single event in 4 billion years. If that transition is genuinely rare, if it requires an extraordinary confluence of circumstances that we simply got lucky enough to experience, then complex life may be far less common than the sheer number of planets in the universe might suggest. A third class of resolutions is more disturbing. It suggests that intelligent life arises relatively commonly, but something tends to stop it from surviving or expanding before it can make its presence known across cosmic distances. This is the concept of the Great Filter, a term coined by economist Robin Hanson in 1998. The Great Filter is whatever step in the development of a civilization is so difficult, so improbable, or so dangerous that almost no species gets past it. Something filters civilizations out before they can spread through the galaxy. The question, the one that keeps a certain kind of thinker awake at night, is whether the Great Filter is behind us or ahead of us. If it is behind us, if the extraordinarily difficult step was something that already happened in our evolutionary history, like the origin of life itself, or the emergence of eukaryotic cells, or the development of multicellular organisms, or the evolution of language and abstract reasoning, then we may be genuinely special. We may have already passed through the filter that eliminates most potential civilizations. The silence around us would reflect the rarity of having gotten this far, and our future, while uncertain, would be open. If the Great Filter is ahead of us, if there is something that technological civilizations reliably encounter and almost never survive, then the silence takes on a different and far darker character. Every civilization that arose before us encountered something that ended it before it could spread and signal across the galaxy, and we will presumably encounter that same thing. What could the Great Filter ahead look like? The candidates are uncomfortably familiar: engineered pathogens, nuclear war, climate catastrophe severe enough to collapse the agricultural and technological infrastructure of a civilization, the development of artificial intelligence that does not align with the interests of its creators, the depletion of the energy and material resources needed to maintain an advanced technological society before the transition to sustainable alternatives is complete. These are not science fiction scenarios. They are recognized risk categories that serious researchers at institutions like the Future of Humanity Institute at Oxford, the Machine Intelligence Research Institute, and the Centre for the Study of Existential Risk at Cambridge have spent careers analyzing. The possibility that technological civilizations have a characteristic lifespan, that something about the combination of intelligence, technology, and competitive instincts tends to produce self-termination within a certain window, is taken seriously as a scientific hypothesis, not just a philosophical worry. And the Fermi paradox gives that hypothesis a kind of terrible empirical support. If civilizations regularly survived and spread through the galaxy, we would expect to see evidence of them. We do not. That absence could mean they are rare to begin with, or it could mean they do not tend to last. There is a fourth resolution that I find particularly fascinating, and it connects directly back to everything this video has been about. Directly back to the speed of light. Perhaps civilizations do not spread through the galaxy physically. Perhaps they communicate. Perhaps the universe is filled with signals, with conversations, with knowledge, with the accumulated understanding of civilizations far older than ours, and we simply have not found the right channel yet. Because here is a thought experiment worth sitting with. If you were a civilization a billion years more advanced than we are, a civilization that had fully come to grips with the realities of interstellar distances and the light speed limit, would you spend your energy trying to physically colonize every star system within reach? Or would you invest in communication, in building a galaxy-spanning network of information exchange that travels at the maximum possible speed, light speed, and makes the physical barriers of distance less relevant than the informational ones? A radio signal, a laser pulse, a modulated beam of any electromagnetic radiation travels at the speed of light. It is the fastest thing in the universe. You cannot move your body across 4 light years in less than 4 years, but you can send a message across 4 light years in exactly 4 years. You can send a book, a library, an entire civilization's accumulated knowledge, compressed, encoded, beamed outward at the speed of light to every star within range. Maybe the universe is not silent at the level of physical presence, but full at the level of information. Maybe the galaxy is saturated with signals we have not yet recognized as signals. Maybe the search has been looking in the wrong frequency, the wrong modulation, the wrong direction, the wrong timescale. The physicist and SETI researcher Claudio Macon has proposed that the optimal frequency for interstellar communication might be a specific value derived from fundamental constants of nature, a frequency that any technologically advanced civilization would be able to calculate independently. Others have proposed that gravitational waves, neutrinos, or as yet undiscovered physics might provide communication channels invisible to our current instruments. We do not know. And that uncertainty, that genuine, honest, evidence-backed uncertainty is different from ignorance. It is the productive uncertainty of a search still in its early stages. A search that has been running for 60 years on a planet whose technological species has existed for a few 100,000 years in a universe 13.8 billion years old. We are not even close to having searched long enough or broadly enough to draw confident conclusions. But here is the connection to the light speed limit that I want you to hold on to, because it is subtle and profound, and most discussions of the Fermi paradox miss it entirely. If the speed of light is truly the maximum speed at which information and influence can travel through the universe, and all current evidence strongly suggests it is, then the universe is fundamentally, structurally local, not just in the sense that things far away are hard to reach, but in the sense that causal influence, the ability of one thing to affect another, is strictly limited by the time it takes light to cross the intervening distance. A civilization on the other side of the Milky Way, 50,000 light years from Earth, could not possibly know we exist today, not because we are hiding, but because the light from our earliest radio transmissions, which have been spreading outward at the speed of light since the early 20th century, has only traveled about 120 light years from Earth. It has not come close to reaching most of the galaxy. The earliest evidence of our technological existence, the first radio waves leaking from our planet, is currently passing through a sphere of space containing perhaps a few thousand stars. Out of 200 to 400 billion in the Milky Way alone, we are, in terms of our electromagnetic footprint, extraordinarily new and extraordinarily local. We have only been technically detectable for about 120 years. On a galactic timescale, that is less than a heartbeat, and the same argument applies in reverse. Civilizations that arose and went silent, that broadcast for 1,000 years and then stopped, for whatever reason, might have sent signals that have already passed through our region of space before we were capable of receiving them. Signals that came and went before we built our first radio telescope, before we even understood what radio waves were. The light speed limit does not just make physical travel between stars brutally difficult. It makes the entire project of cosmic communication a game of patience measured in geological time. Signals take years, decades, centuries, millennia to cross interstellar distances. Conversations happen across generations. By the time a response to our first detected alien signal could be composed and returned, everyone alive today would be dead, and their grandchildren's grandchildren would be reading the reply. The universe enforces a kind of radical patience on any civilization ambitious enough to look beyond its own star system. And patience, measured in generations, in centuries, in millennia, may be one of the rarest and most valuable properties a technological civilization can possess. There is one more resolution to the Fermi paradox that I want to mention, because it is the one that the physicists and cosmologists I most respect tend to return to when pressed for their honest intuition. It is called the dark forest hypothesis, and it was popularized by the Chinese science fiction author Liu Cixin in his extraordinary trilogy that begins with the novel The Three-Body Problem. But the underlying logic is not science fiction. It is game theory applied to an environment, the galaxy, where the light speed limit creates fundamental uncertainty and asymmetric risk. The argument works like this. In a universe where civilizations cannot travel between stars quickly and where communication takes years to decades, any two civilizations encountering each other face a profound uncertainty. They cannot verify each other's intentions in real time. They cannot negotiate in real time. They cannot respond to aggression in real time. In that environment of radical information lag, the game-theoretic logic of survival might push civilizations towards silence and concealment rather than broadcast and contact. Broadcasting your existence is, potentially, announcing your location to every predatory civilization within signal range. In a universe where we cannot know the intentions of others, where we cannot defend against threats that travel at light speed, where any response to an aggressive signal takes decades to arrive, the safest strategy might simply be to be quiet, to listen without transmitting, to hide. On this view, the universe is not empty of civilizations. It is full of them, all hiding from each other, all maintaining silence for the same reason, all trapped in a cosmic prisoner's dilemma, where broadcasting feels like risk and silence feels like safety. I am not saying this is the answer. I am not sure anyone can say with confidence what the answer is. But the dark forest idea has a particular clarity that stays with you. Because if it is true, if the silence of the cosmos is the sound of civilizations hiding rather than the sound of emptiness, then our own recent broadcasts, our century of radio and television and radar leaking into space at the speed of light, represents something remarkable. A species young and naive enough, or brave and idealistic enough, to announce itself anyway. Whether that is foolish or admirable probably depends on what is actually out there. And here is the thing about all of these resolutions: the rare earth, the great filter, the communication hypothesis, the dark forest, that I find most honest and most important to say directly. We do not know which one is right. We do not even know if the right answer is among them. Science is not a collection of settled truths on a shelf. It is an ongoing negotiation with reality, driven by evidence, constrained by logic, advanced by imagination and humility in equal measure. What we know is this: the universe is ancient, it is vast, it is almost certainly not empty of the ingredients for complexity and life. The light speed limit makes it structurally isolated at the level of physical travel, and the silence we have observed so far is consistent with many different underlying realities, some comforting, some troubling, some genuinely unknown. What we also know is this: we are here. We are asking the question. We are the universe wondering whether it is alone. And however that question is ultimately answered, the asking of it is itself something extraordinary. A universe that contained no mind capable of wondering about its own loneliness would be in some sense a lesser universe, not in any mystical way, but in the straightforward sense that curiosity and consciousness and the desire to understand are remarkable phenomena that took nearly 14 billion years to produce, and that deserve to be taken seriously as part of the cosmic inventory. You are not a passive observer of the universe, you are a product of it, and the questions you carry are as real and as significant as any star or galaxy or quantum field. Let us begin with something small, not a galaxy, not a light year, not a quantum field or a relativistic equation or a cosmic horizon. Something small, something close, something you have probably done without thinking about it too deeply, because it is so ordinary that it barely registers as remarkable anymore. You have looked up at the night sky. Maybe it was from a backyard, or a rooftop, or a field somewhere away from the city lights, where the Milky Way was actually visible, that pale, diffuse band of light stretching from horizon to horizon. The combined glow of hundreds of billions of stars, too distant and too numerous to resolve individually, compressed by distance into something that looks almost like fog. Maybe you were a child and someone pointed out a constellation. Maybe you were older and it just happened. You stepped outside on a clear night and there it was, the sky doing what it has always done, indifferent and magnificent. That moment, that upward glance, is one of the oldest human experiences in existence. Our ancestors did it around fires on the African savannah 300,000 years ago. They did it from the decks of ships crossing the Pacific. They did it from the tops of pyramids and the openings of caves and the rooftops of ancient cities whose names we have mostly forgotten. The sky was always there. It was always doing this, wheeling overhead in its slow nightly arc, constant and mysterious and impossible to ignore. And for most of human history, looking up was all we could do. Now consider what we have added to that upward glance in the last few hundred years. Not the last few thousand, the last few hundred. In the blink of a cosmic eye, we went from pointing at lights in the sky and weaving stories about them to understanding, with mathematical precision, with experimental confirmation, with instruments of almost unimaginable sensitivity, what they actually are. Those lights are nuclear furnaces fusing hydrogen into helium in their cores, producing energy through Einstein's equation, radiating that energy outward for billions of years. Some of them are younger than our sun, some are older, some have already died, and we are still seeing their light, a ghost image from a star that no longer exists. Some are orbited by planets. Some of those planets have atmospheres. Some of those atmospheres might contain molecules that living chemistry produces. We know all of this. We worked it out. With telescopes and mathematics and peer review and generations of patient, cumulative effort by human beings who spent their lives asking questions about lights in the sky. That is extraordinary. That is, if you let yourself feel it properly, one of the most extraordinary things about being the kind of creature we are. But here is the tension that sits at the heart of this entire video, the tension that all 9 parts have been circling around and that I want to name directly now. We understand the stars better than any species in the known history of this planet has ever understood anything. We have mapped the cosmic microwave background, the oldest light in the universe. We have detected gravitational waves from black holes merging 1 billion light-years away. We have imaged the shadow of a supermassive black hole at the center of a galaxy 55 million light-years from Earth, using a telescope the size of the planet itself. We have sent 5 spacecraft beyond the edge of our solar system, and we cannot get to the nearest star, not in any human lifetime, not even close. The nearest star is 4.2 light-years away, approximately 40 trillion kilometers, and the fastest spacecraft we have ever launched would take over 70,000 years to reach it. The most ambitious, credible proposal for crossing that distance, Breakthrough Starshot's laser-propelled postage stamp spacecraft, would take 20 years, but carries no human being, cannot decelerate at the destination, and does not yet exist in buildable form. The gap between what we know and what we can do is vast, and it is not closing quickly. And I want to sit with that tension honestly for a moment, rather than rushing to resolve it with optimism or dismiss it with resignation, because the honest, nuanced, fully inhabited version of this situation is more interesting and more instructive than either of those shortcuts. The history of human ambition in the face of impossible seeming distances is worth reflecting on, because it is not a simple story of inevitable triumph. It is a story of genuine difficulty, genuine failure, genuine loss, and genuine hard-won progress. For most of human history, the world was effectively much larger than it is today. Not physically larger, the planet is the same size it has always been, but experientially, informationally, practically larger. A journey from one side of a continent to the other took months. A journey across an ocean took weeks or months and killed a significant fraction of the people who attempted it. The interior of continents remained unmapped and unknown to outside civilizations for centuries after the maps of coastlines were drawn. In 1492, just over 500 years ago, which is nothing by any measure except a human one, Christopher Columbus crossed the Atlantic Ocean in a wooden ship powered by wind, with no GPS, no radio, no accurate understanding of the longitude of his destination, no way to call for help if something went wrong, and no certainty that there was anything on the other side except empty ocean. He and his crew were operating at the absolute edge of the possible for their time. They made it, not elegantly, not without fear or near disaster or significant navigational error. Columbus died believing he had reached Asia rather than a previously unknown landmass. But they crossed the distance in 1969, less than 80 years ago, within the lifetimes of people still alive today. Human beings traveled 384,000 kilometers through space, landed on the surface of the moon, walked around on it, collected rocks, planted a flag, and came home. 12 people walked on the moon. The last of them, Gene Cernan, left the lunar surface on the 14th of December, 1972, over 50 years ago now, and no human being has been back since. The arc from wooden sailing ships to lunar landings covers 500 years. 500 years from Columbus crossing the Atlantic to Armstrong stepping onto the moon. 500 years from the edge of the known world to the surface of another world. In the context of that arc, in the context of what human beings have already accomplished in the span of recorded history, which itself is only a tiny fraction of our species' existence, the challenges of interstellar travel are daunting, but not categorically different in kind from the challenges that have been overcome before. They are harder, they require longer timescales, they may require civilizational coordination on a scale we have not yet achieved. But they are not magic, they are not prohibited by logic. They are engineering problems and physics problems and social problems, and human beings, against all reasonable expectation, turn out to be remarkably good at engineering problems and physics problems and social problems, given enough time and enough motivation. There is a concept in the philosophy of science that I find genuinely useful here. It was articulated most clearly by the physicist and philosopher David Deutsch in his book The Beginning of Infinity, published in 2011. Deutsch distinguishes between problems that are prohibited by the laws of physics, things that genuinely cannot be done, like transmitting information faster than light or extracting more energy from a process than thermodynamics permits, and problems that are merely difficult, hard, currently beyond our reach, requiring knowledge and technology and resources we do not yet have. His argument is that every problem that is not prohibited by the laws of physics is in principle solvable, given enough knowledge, not given enough time or enough effort or enough resources in some fixed sense, given enough knowledge. Because knowledge is the transformative ingredient. Knowledge changes what is possible. Knowledge turns previously impossible seeming things into engineering problems. Knowledge is the thing that separates the world. Columbus sailed in from the world that launched Apollo 11. On Deutsch's framework, the challenges of interstellar travel, the radiation, the energy requirements, the biology, the distances, the timescales, are overwhelmingly problems of insufficient knowledge rather than prohibitions of physics. We do not yet know how to build a magnetic shielding system robust enough to protect human beings across decades of deep space travel. We do not yet know how to produce and store antimatter at mission-relevant scales. We do not yet know how to build a laser array of sufficient power and coherence to accelerate a gram-scale spacecraft to 20% of light speed. But none of those things are prohibited. They are simply beyond the current frontier of what we know. And the frontier of what we know has been advancing continuously for as long as human beings have been paying attention to the world around them. This is the part of the story where I want to talk about time, not relativistic time dilation. We covered that in part 2. Human time, generational time, the time scale on which civilizations change. We tend to think about the future in terms of our own lifetimes. What can be achieved in the next 5 years, the next 10, the next 50? It is a natural cognitive bias. Our own mortality sets the horizon of our immediate concern, but it is a profoundly misleading timescale for thinking about what humanity is capable of, because the most important achievements of our species have almost never been the work of a single lifetime. They are the work of generations, each one building on what the previous one left behind. The cathedral builders of medieval Europe understood this viscerally. The great cathedrals of Chartres and Cologne and Notre Dame took 100, 200, 300 years to build. The architects who drew the first plans knew they would never see the finished structure. The craftsmen who carved the foundation stones knew their grandchildren would still be working on the walls. They built anyway. They passed the plans forward. They trusted that what they began would be continued. Science works the same way. Newton built on Galileo. Einstein built on Maxwell. The physicists who detected gravitational waves in 2015 with the LIGO detector built on a theoretical framework developed by Einstein in 1916 and an experimental program that had been running for decades before the first detection. The achievement was 100 years in the making. Interstellar travel, real interstellar travel, human interstellar travel, is a cathedral project. It is not a project for a single administration, a single generation, a single century. It is a project for a species, for a civilization that decides, collectively and consciously, that this is something worth working toward across the timescale required to make it real. That decision has not been made yet, not formally, not institutionally, not with the kind of sustained commitment and resource allocation that the Manhattan Project or Apollo or the Human Genome Project represented. Those programs achieved their goals in years or decades because they had that commitment, that focus, that resource. Interstellar travel needs something analogous, but calibrated to a civilizational timescale rather than a political one. It needs the kind of institutions that can outlast elections and economic cycles and the short-termism of quarterly thinking. It needs the kind of patience that the cathedral builders had, the willingness to work on something whose completion you will not live to see because the work matters regardless. Whether our civilization is capable of that kind of sustained, multi-generational commitment is honestly an open question. We have shown we can do it in limited domains. Science itself is the best example. A multi-generational project of knowledge accumulation that has been running continuously for at least 500 years. But we have also shown a persistent tendency to defund, abandon, and forget long-term projects when short-term pressures intrude. The stars will require the better version of us, the more patient, more cooperative, more far-sighted version. Whether that version is available, whether we can grow into it, is one of the most important questions of the coming centuries. I want to talk about something that does not come up often in discussions of space exploration, but that I think is essential to understanding why it matters beyond the purely scientific. It is the question of what the attempt does to us. Not what interstellar travel will eventually achieve when it is realized, the knowledge gained, the resources accessed, the existential insurance of becoming a multi-star species. What the attempt itself does to us right now in the trying, because the history of human exploration is not just a history of destinations reached. It is a history of who we became in the reaching. The navigation technologies developed for ocean crossing became the foundations of global trade and communication. The miniaturization and reliability engineering developed for spacecraft became the microelectronics that put a supercomputer in your pocket. The life support systems designed for astronauts produced medical technologies used in hospitals worldwide. The image processing developed to sharpen photographs from deep space telescopes is now used in MRI and CT scanners. The attempt to do hard things produces capabilities that propagate outward into every domain of human life. The attempt to reach the stars, even if that attempt takes centuries, even if no human being alive today is ever launched toward another sun, is already producing knowledge, technology, motivation, and perspective that changes what is possible here on the planet we actually live on. And there is something else the attempt does, something harder to quantify, but no less real. It changes the story we tell about ourselves. A species that is trying to reach the stars is a species with a future worth imagining, a species that has given up on the cosmos, that has looked at the distances and the physics and said it is simply too hard, not worth attempting, has contracted its sense of possibility in a way that affects everything else it does. The willingness to attempt genuinely difficult things, to commit to projects that outlast individual lifetimes, to dream at the scale the universe actually operates on rather than the scale our anxieties constrain us to. These are not luxuries. They are symptoms of civilizational health. Carl Sagan, who spent his life making the case for the importance of space exploration with an eloquence that has rarely been matched, put it this way. He argued that the exploration of the cosmos is a necessary hedge against the tendency of earthbound civilizations to turn inward, to focus on internal conflicts, to forget that their problems, however real, are playing out on a tiny stage in a vast universe. The perspective of the cosmos, the experience of seeing Earth from a distance, of understanding our actual scale and situation, is a corrective to the provincialism that makes human beings do terrible things to each other over resources and territories and beliefs that, from any cosmic vantage point, are barely distinguishable. The famous photograph taken by Voyager 1 on the 14th of February 1990, requested by Sagan himself, taken from a distance of approximately 6 billion kilometers, shows Earth as a pale blue dot, less than a pixel in size, suspended in a beam of scattered sunlight. Sagan's meditation on that image is one of the most important things ever written about what we are and where we live. He wrote, "That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies and political empires, all hunters and foragers, all heroes and cowards, all creators and destroyers of civilization, all kings and peasants, all young couples in love, all mothers and fathers, all inventors and explorers, all teachers of morals, all corrupt politicians, all superstars, all supreme leaders, all saints and sinners in the history of our species live there on a mote of dust suspended in a sunbeam. A mote of dust suspended in a sunbeam, and yet, from that mote of dust in the 100,000 years or so, that our species has been anatomically modern, and in the 500 years since science as a systematic method began, we have figured out the age of the universe, the nature of stars, the composition of black holes, the structure of DNA, the mechanism of evolution, the quantum nature of matter, and the geometry of space-time. We have done all of that from a pale blue dot. Imagine what we might figure out if we could look back at it from somewhere else. There is a physicist whose work I want to mention here, because I think it represents one of the most honest and most beautiful ways of thinking about what this whole endeavor means. Freeman Dyson, who died in 2020 at the age of 96, having spent a lifetime at the frontier of theoretical physics, contributing to quantum electrodynamics, proposing the theoretical framework for the Dyson sphere, working on the early nuclear pulse propulsion studies for Project Orion, and writing with extraordinary clarity about the relationship between science and the human condition, wrote an essay in 1979 called Time Without End, Physics and Biology in an Open Universe. In it, he explored the question of whether life and intelligence could survive indefinitely in an ever-expanding, ever-cooling universe. His conclusion was cautiously optimistic. He argued that life, if it was sufficiently adaptable, could in principle continue indefinitely, slowing its metabolism to match the cooling universe, hibernating through long cold periods, finding ways to sustain thought and experience across timescales that dwarf the current age of the cosmos. The essay is remarkable not because its specific conclusions have all held up. Subsequent work on the fate of the universe has complicated the picture considerably, but because of what it represents. A physicist choosing to spend his intellectual energy on the question of how life might persist and flourish against the longest timescales the universe offers, not accepting the heat death of the universe as the end of the story, asking whether there is a way around it, or through it, or beyond it. That impulse, that refusal to accept the final answer without checking every door, is the same impulse that drives the interstellar propulsion researchers and the SETI scientists and the astrobiologists and the cosmologists. The same impulse that drove Columbus into the Atlantic and Armstrong onto the moon. It is the impulse that makes us human, the one that looks at a horizon and wants to know what is on the other side of it. So let us return, one final time before our closing, to the question this video has been asking from the beginning: why would traveling at light speed destroy you before you even arrive? We have covered the answer from a dozen different angles now. The interstellar medium, the cosmic gravel of gas and dust and cosmic rays that would sandblast your spacecraft and irradiate your body, the relativistic effects, the blue shift of incoming radiation from across the electromagnetic spectrum, turning visible light into deadly gamma rays, the mass increase, the mathematical impossibility of actually reaching light speed without requiring infinite energy, the Higgs field and the Unruh radiation, the biological degradation, the bone loss, the muscle atrophy, the immune suppression, the vision impairment, the psychological erosion of isolation and confinement across decades. But I think the deepest answer to the question is not any of those things individually. The deepest answer is this: the universe is not built to be crossed quickly. It is built at a scale that takes time, real time, enormous time, generational time to traverse. The light speed limit is not an arbitrary obstacle placed between us and the stars out of some cosmic cruelty. It is a fundamental feature of the structure of space-time itself, a feature that shapes everything about how the universe works, how information propagates, how causality operates, how the past relates to the future. To try to exceed it is not just to attempt an engineering feat. It is to attempt to rewrite the architecture of reality. And reality, as we have been discovering for the past century of physics, is more robustly itself than we are. The universe does not bend to our impatience. It does not make exceptions for species that really want to get somewhere in a hurry. It has its rules, its structure, its constants. And those constants are what they are not to inconvenience us, but because they are part of what makes the universe coherent, stable, knowable. In a universe where light traveled infinitely fast, there would be no cosmic horizon, no expansion visible in the redshift of distant galaxies, no time delay between emission and detection, no finite speed of information that gives space-time its causal structure. A universe without the light speed limit would be a fundamentally different kind of universe, and it is not obvious it would be one capable of supporting the complexity and structure that life requires. The constraint that makes the stars unreachable is part of the same physical structure that makes stars exist in the first place. And here, finally, is the thing I most want to leave you with. The fact that we cannot reach the stars easily does not make us small. It does not diminish us. It does not represent some failure or limitation of the human spirit. It tells us where we are in the story. We are early. We are young. We are the first iteration of something that is still working out what it is and what it can become. We are a species that 66 million years after a rock fell from the sky and ended the age of dinosaurs, developed the mathematics to describe the motion of that rock, to understand where it came from, to predict when the next one might arrive, and to begin thinking about what to do about it. We are a species that, 4 billion years after life first appeared on this planet as single-celled chemistry in a warm, shallow sea, produced creatures capable of understanding that 4 billion year history and telling the story of it to each other. We are a species that looked at a universe incomprehensibly larger and older than anything our intuitions were evolved to handle, a universe of 2 trillion galaxies, of supermassive black holes and dark matter and dark energy and quantum fields and curved space-time, and said, we want to understand this, we are going to figure this out, and then actually started to. That is not a small thing. That is, as far as we know, an extraordinarily rare thing in the universe. The stars are far away. The light speed limit is real. The biology of space travel is brutal. The physics is uncompromising. All of that is true, and we should not pretend otherwise. But we are here. We are asking. We are looking up. And the looking up is itself a kind of reaching, a way of touching, with the mind if not yet with the hand, the vast and beautiful and indifferent cosmos that made us. That is enough for now. It is, given where we are in the story, everything. Let us talk about what you can do, right now, today, not as a physicist or an astronaut or a mission planner, as a person who has just spent this much time thinking about the stars and what they mean. The first thing is to look up. Actually look up, not metaphorically. Go outside on a clear night and look at the sky. If you live somewhere with light pollution, go somewhere you do not. The Milky Way is still there. The stars have not gone anywhere. And looking at them with the knowledge you now carry, with the understanding of what they are, what the light you are seeing has gone through to reach your eyes, what the silence between them contains, is a different experience than looking at them in ignorance. It is richer, stranger, more vertiginous and more beautiful than the naive wonder of childhood, which was beautiful enough. The second thing is to stay curious. Not about space specifically, about everything. Because the reason we understand the stars is not that a special class of people called scientists went off and figured it out in isolation. It is that human curiosity, expressed across thousands of years by people from every culture and every background, asking questions and sharing answers, produced the cumulative structure of knowledge that we now inhabit. Your curiosity is part of that. It always has been. Every time you ask why, every time you follow a question to its source, every time you refuse to accept a comfortable non-answer, when a harder true one is available, you are contributing to the oldest and most important human project. The third thing is to think long, to practice the kind of thinking that the cathedral builders had, that sees beyond the horizon of your own lifetime to the structure being built across generations. The problems that matter most, climate stability, the development of artificial intelligence, the long-term resilience of civilization, the eventual expansion of life beyond our planet, are all multi-generational problems. They require not just individual action, but institutional memory, sustained commitment, and the willingness to work on something because it matters rather than because you will personally see the payoff. And the fourth thing, the one that I think ties all of the others together, is to hold the paradox of being a small, short-lived creature in an incomprehensibly large and ancient universe. The paradox of caring deeply about things that the cosmos does not notice. The paradox of reaching for stars that will destroy you if you approach them too quickly. The paradox of being made of the universe, curious about the universe, unable to fully access the universe, and unable to stop trying anyway. That paradox is not a problem to be solved. It is a condition to be inhabited. It is, in a profound sense, what it means to be human in the cosmos as it actually is, and inhabiting it honestly, without collapsing it into false comfort on one side or nihilistic despair on the other, requires exactly the qualities that science at its best embodies: rigor and wonder, humility and ambition, the willingness to be wrong and the determination to keep asking. Here is what this video has really been about. It has not been about why you cannot travel at light speed. The physics of that is real and important and worth understanding, and I hope we have done it justice across these 10 parts. But the physics was never the point. The physics was the doorway. What this video has really been about is the question of what we are. We are creatures built from the residue of exploded stars, living on a rocky planet orbiting a middle-aged star in the outer arm of a spiral galaxy, in a universe 13.8 billion years old, and at least 93 billion light-years across in the observable volume alone. We are alive for perhaps 80 or 90 years. We are conscious for even less of that. We are capable of understanding the laws that govern the universe that made us. We cannot travel at light speed. We cannot cross the interstellar distances in any human lifetime with current technology. We cannot see beyond the cosmic horizon. We cannot communicate with the civilizations, if they exist, that lie beyond the reach of our signals or theirs. And yet, we sent Voyager 1 past the edge of the solar system, and it is still talking to us, 50 years later, from 23 billion kilometers away, on the power of a generator producing roughly the same watts as a dim light bulb. We imaged a black hole 55 million light-years away using a planet-sized telescope assembled from radio dishes on 6 continents. We detected the gravitational ripples of 2 black holes merging over 1 billion years ago using instruments sensitive enough to measure a change in distance 1,000th the diameter of a proton. We decoded the 3 billion-letter instruction manual of human life written in 4 chemical letters in the nucleus of every cell in your body. We did all of that, us, this species, this experiment in consciousness and curiosity that the universe appears to have stumbled upon somewhere around 300,000 years ago on the 3rd planet from an ordinary star. If we have come this far in 300,000 years, in 500 years of systematic science, the question of where we might be in another 500, another 5,000, another 500,000 years is not answerable. It is not answerable because the knowledge we will have then is by definition not something we can project from here. The shape of what is coming is hidden in the same way that the shape of quantum mechanics was hidden from Newton. The shape of DNA was hidden from Darwin. The shape of cosmic expansion was hidden from Einstein. What we can say, what the evidence actually supports, is that the trajectory is real, the accumulation of knowledge is real, the expansion of what is possible, generation by generation, is real. And the desire that drives it, that restless, irrepressible, fundamentally and specifically human desire to understand, shows no sign of fading. The stars are not waiting for us. They do not know we exist. They will burn for billions of years, whether we reach them or not, indifferent and magnificent, fusing hydrogen in their cores, scattering their heavier elements into the galaxy when they die, seeding the raw material of future worlds and future life in the same quiet, unhurried way they have always done. But we know they are there. We know what they are. We know how far away they are and what it would take to cross that distance, and why the crossing is so brutally difficult, and what it might one day look like to begin to attempt it seriously. And we are, right now, today, in this imperfect, struggling, brilliant, infuriating, beautiful civilization on this pale blue dot, the only part of the universe that knows any of that. That is not a small thing. That is everything. The stars did not ask to be understood. We chose to try, and that choice, made again and again, generation after generation, by curious creatures with finite lives and infinite questions, is the most human thing there is. We cannot travel at light speed. Not yet. Perhaps not ever. But we looked up. We measured the distance. We understood why it is hard. And we are still reaching. That is how the story continues. And if your mind is still out there, still drifting between the stars, I have one more journey for you. Click the video on your screen right now. We explore what would actually happen on a journey to Proxima Centauri. And trust me, after everything we just covered, you are ready for it. It will blow your mind all over again. Let's meet there.